Welcome to Dynadust, where ancient Earth comes alive and your thoughts can settle. Tonight we drift back to a frozen world, a time when mammoths roamed, saber-tooths hunted, and ice shaped the planet itself. Before we begin, we would love to know where in the world you're watching from and what time it is for you right now. Let us know in the comments below, and settle in for a relaxing journey. An ice age is a prolonged period in Earth's history marked by significant global cooling, during which vast ice sheets expand across large portions of the continents. Unlike a typical winter or seasonal cold spell, which lasts for months and affects localized regions, an ice age encompasses thousands or even millions of years, fundamentally transforming the planet's climate, geography, and ecosystems. During these extensive intervals, the planet's average temperatures drop markedly, allowing the accumulation of ice to extend well beyond the polar regions, reaching into mid-latitudes and shaping the landscape in profound ways. A key distinction between an ice age and ordinary cold periods lies in scale and duration. Seasonal winters are relatively short-lived, driven by Earth's orbit and tilt, causing predictable cycles of cold and warmth annually. In contrast, ice ages involve sustained global cooling, with ice sheets persisting for thousands of years, often punctuated by intermittent warmer periods known as interglacials. These interglacial phases temporarily reduce ice coverage, but the overarching glacial cycles remain a defining feature of ice ages. The processes driving ice ages are complex, involving shifts in Earth's orbit, known as Milankovich cycles, that influence the distribution and intensity of sunlight reaching the planet. These variations gradually alter climate patterns, encouraging ice sheet growth or retreat over extended timescales. Other factors, such as atmospheric composition, volcanic activity, and ocean currents, also play critical roles in initiating and terminating glacial periods. Understanding the distinction between an ice age and seasonal cold spells illuminates the incredible scale of Earth's climate system. While a winter may bring snow and cold to a region, an ice age reshapes entire continents, creating new landforms and influencing the evolution life over millennia. Recognizing these differences underscores the importance of studying Earth's climatic history to appreciate the extraordinary forces that have sculpted our planet's surface. As we delve into the timeline of Earth's most recent ice age, it becomes essential to explore when these colossal climate shifts occurred and the key periods that define their progression. When did the most recent ice age occur, and what are the key timeframes involved in its timeline? The most recent ice age, often referred to as the Quaternary glaciation, began approximately 2.58 million years ago and continues into the present day, though it has experienced various cycles of advance and retreat over this extensive period. This epoch marks the beginning of a series of glacial and interglacial phases that have dramatically shaped Earth's surface and climate history. The timeline of this ongoing ice age is punctuated by significant fluctuations, with the most recent major glacial period, known as the last glacial maximum, peaking around 20,000 years ago. During this peak, vast ice sheets blanketed much of North America, Northern Europe and Asia, transforming the landscape and ecosystems. The transition from glacial to interglacial conditions is marked by complex climatic shifts, driven by variations in Earth's orbit, axial tilt, and precession, collectively known as Milankovich cycles. These variations influence the distribution and intensity of solar radiation reaching Earth's surface, setting off cyclical patterns of cooling and warming. The end of the last glacial period about 11,700 years ago ushered in the current interglacial, known as the Holocene, which has provided relatively stable climatic conditions conducive to human development and civilization. Throughout this timeline, the boundaries between glacial and interglacial phases are characterized by significant environmental transformations. Advances in ice sheet coverage, sea level fluctuations, and shifts in flora and fauna are hallmarks of these cycles. The glacial phases are marked by extensive ice sheet expansion, which lowers sea levels as vast volumes of water become locked in ice. Conversely, interglacial periods see the retreat of ice sheets, rising sea levels, and warmer global temperatures. These alternating phases have been instrumental in shaping the Earth's topography, influencing ocean currents, and driving evolutionary adaptations among species. Understanding these key timeframes helps contextualize the dynamic nature of Earth's climate system. As scientists continue to refine the chronology of these cycles, they reveal not only the Earth's climatic past, but also offer insights into the ongoing processes that influence our current climate. Exploring the primary characteristics that define an ice age allows us to appreciate the profound environmental shifts that have occurred over millions of years, setting the stage for a deeper understanding of the climatic and environmental signatures that distinguish such periods. At the heart of an ice age lies a distinctive climate marked by persistent, widespread cooling. These periods are characterized by a significant drop in global temperatures, often several degrees Celsius below the average of interglacial phases, leading to the expansion of continental ice sheets across vast regions. Such cooling is driven by complex interactions among Earth's orbit, axial tilt, and solar radiation, factors collectively known as Milankovich cycles, which modulate the amount of sunlight reaching different parts of the planet. These cyclical variations set the stage for prolonged cold spells that can last tens of thousands to hundreds of thousands of years. Environmental conditions during an ice age are equally defining. Reduced temperatures cause polar ice sheets to grow and extend far beyond their usual limits, covering large portions of North America, Eurasia, and other high-latitude areas. This expansion alters the Earth's albedo, its reflectivity, causing more sunlight to be reflected back into space, thus reinforcing the cooling trend. Meanwhile, glaciers become more extensive and thicker, carving out deep valleys and shaping the landscape through relentless erosion. The cold climate also leads to a decline in vegetation in many regions, transforming lush landscapes into tundra or desert-like environments, with ecosystems adapting to harsh, resource-scarce conditions. Precipitation patterns shift dramatically as well, with some regions experiencing increased snowfall that feeds the ice sheets, while others become increasingly arid. The combination of colder temperatures and altered precipitation patterns results in a landscape sculpted by ice, with features such as deep fjords, U-shaped valleys, and moraines. Moraine deposits marking the edges of retreating glaciers. Understanding these climatic and environmental signatures provides crucial insights into the nature of ice ages. They set the foundational context for studying the remnants of these cold epochs, preserved in Earth's geological record, which, in turn, allows scientists to reconstruct the history of past climate fluctuations. This deep connection between climate, environment, and the physical landscape forms the basis for exploring how researchers decode Earth's glacial past through geological evidence. To uncover the history of Earth's ice ages, scientists rely on a diverse array of evidence that acts as a silent record etched into the planet's surface. One of the primary tools in this pursuit is the study of glacial deposits, vast layers of till, gravel, and stratified sediments left behind by glaciers as they advance and retreat. These deposits, often found in moraines and outwash plains, serve as tangible markers of past glacial activity. By analysing their composition, location, and stratigraphy, researchers can reconstruct the extent and timing of ice sheet coverage over millennia. Another critical piece of evidence comes from the examination of landforms such as U-shaped valleys, fjords, and drumlins, which are shaped distinctly by glacial erosion. These features reveal the direction and intensity of ice movement, providing clues about the volume and reach of glaciers during different periods. Additionally, scientists study the distribution of erratics, large boulders transported by glaciers far from their original bedrock sources, offering insights into the pathways and dynamics of ice flow. Beyond surface features, the study of sediments within lakes and oceans offers a wealth of information. Sediment cores extracted from these environments contain layers of material deposited over time, including pollen, ash, and isotopic signatures. Isotope analysis, particularly of oxygen isotopes in glacial ice and marine sediments, enables scientists to determine variations in global temperatures and ice volume. These isotopic ratios fluctuate with the advance and retreat of ice sheets, serving as a precise chronometer for glacial cycles. Fossil evidence also complements physical data, as shifts in flora and fauna distributions reflect climatic changes associated with glaciation. When combined with radiometric dating techniques, such as carbon dating of organic materials or uranium series dating of minerals, These diverse lines of evidence help establish a timeline for past ice ages with remarkable accuracy. Through the integration of these geological, chemical, and biological clues, scientists piece together Earth's icy past, revealing patterns of climate change that have shaped the planet's surface over countless millennia. This comprehensive approach provides the foundation for understanding the complex oscillations between glacial and interglacial periods within an ice age. Within the broader framework of an ice age, the alternating phases of glacial and interglacial periods represent distinct climatic states driven by complex interactions among Earth's orbit, atmospheric composition, and ocean currents. During glacial periods, vast ice sheets advance beyond their typical boundaries, covering large portions of North America, Europe, and Asia. These ice sheets can extend hundreds of meters in thickness, profoundly reshaping the landscape. The climate during these times becomes markedly colder, often by several degrees Celsius, as increased ice coverage reflects incoming solar radiation, amplifying cooling, a feedback mechanism known as the albedo effect. This extensive ice coverage acts as a barrier to moisture movement, resulting in decreased precipitation in some regions, which sustains the ice sheet's growth. In contrast, interglacial periods mark intervals of relative warmth that follow the peak of glaciation. During these times, ice sheets retreat significantly, exposing land previously buried beneath ice. Temperatures rise, often by 4 to 8 degrees Celsius compared to glacial phases, fostering conditions more conducive to the development of forests, grasslands, and diverse ecosystems. The melting of ice sheets during interglacials increases the volume of water stored in oceans, leading to elevated sea levels, sometimes by as much as 120 meters relative to glacial maxima. This rise floods coastal plains and reshapes continental margins, creating new habitats and altering oceanic circulation patterns. The transition between these phases is driven by subtle variations in Earth's orbital parameters, known as Milankovich cycles, which influence the distribution and intensity of solar radiation reaching the planet. Changes in greenhouse gas concentrations, especially carbon dioxide and methane, further modulate the climate's response, either amplifying cooling during glacial periods or warming during interglacials. These oscillations have occurred over tens of thousands to hundreds of thousands of years, shaping the planet's climate history and influencing the evolution of Earth's biosphere. Understanding the distinctions between glacial and interglacial periods reveals how Earth's climate system is sensitive to a variety of internal and external factors. This dynamic interplay not only influences terrestrial environments, but also sets the stage for their subsequent effects on global climate patterns and sea levels, which will be explored next. Ice ages exert profound influences on global climate patterns and sea levels, reshaping the planet's environmental landscape over tens of thousands to millions of years. During these periods, extensive ice sheets and glaciers expand across continents, significantly altering the Earth's albedo, the measure of how much sunlight the surface reflects. As ice covers vast regions, more solar radiation is reflected back into space, leading to a cooling feedback loop that sustains and amplifies the cold conditions. This increased reflectivity not only cools local areas, but also affects atmospheric circulation patterns, disrupting typical weather systems and precipitating shifts in climate zones worldwide. The expansion of ice sheets also dramatically impacts sea levels. As water is trapped in massive glaciers and ice sheets, global sea levels decline, sometimes by over 100 meters during the peak of the last glacial maximum. These drops expose continental shelves, creating land bridges that alter migration routes for both humans and animals, and reshape oceanic currents. Conversely, during interglacial periods, times of relative warmth, these ice masses retreat, releasing stored water back into the oceans and causing sea levels to rise. This cyclical pattern of glaciation and deglaciation drives significant changes in coastal environments, ecosystems, and global climate stability. The shifting distribution of ice and water masses influences oceanic and atmospheric circulation, which in turn affect weather patterns and climate variability across the globe. For instance, the redistribution of fresh water from melting ice can weaken or redirect ocean currents like the Gulf Stream, leading to regional cooling or warming episodes. These interconnected processes create a dynamic climate system that oscillates between cold and warm phases, shaping the Earth's environmental history. Understanding how ice ages influence climate and sea levels reveals just part of a broader, intricate puzzle. To grasp the full picture, it is essential to consider what triggers the timing and severity of these glacial cycles, specifically the subtle yet powerful variations in Earth's orbital parameters. What role do Earth's orbital variations play in the timing and intensity of ice ages? Earth's orbital variations are fundamental drivers behind the timing and intensity of ice ages, operating through a cyclical mechanism known as Milankovich cycles. These subtle but persistent changes in the planet's orbit influence the distribution and intensity of sunlight reaching different parts of the Earth, thereby setting the stage for glacial and interglacial periods over tens of thousands to hundreds of thousands of years. There are three primary components of these orbital variations. First, the eccentricity of Earth's orbit fluctuates approximately every 100,000 years, altering the shape of the orbit from more circular to more elliptical. When the orbit is more elongated, the difference between the closest approach to the Sun, perihelion, and the farthest point, aphelion, increases, impacting seasonal contrasts. Second, axial tilt, or obliquity, varies roughly every 41,000 years, changing the angle of Earth's axis relative to its orbital plane. Greater tilt amplifies seasonal differences, making summers warmer and winters colder, which can promote ice sheet growth or melting depending on the phase. Third, the precession of Earth's axis, occurring over approximately 23,000 years, shifts the timing of seasons relative to Earth's position in its orbit, further modulating seasonal and latitudinal insolation patterns. These orbital factors do not act in isolation, but combine to create complex patterns of insolation, the amount of solar radiation received at different latitudes and times of year. When conditions favour cooler summers in the northern hemisphere, ice sheets can advance, initiating or intensifying an ice age. Conversely, periods when insolation increases in these regions tend to promote melting and interglacial warmth. The interplay of these cycles explains why ice ages have occurred in rhythmic, predictable patterns over Earth's history. Understanding how Earth's orbital variations orchestrate these glacial cycles reveals the delicate balance governing our planet's climate system. Recognizing these natural rhythms provides crucial insight into the mechanisms that have shaped Earth's climate over millennia, forming a vital foundation for examining the modern climate change phenomena that challenge us today. Understanding ice ages extends beyond mere curiosity about Earth's distant past. It provides vital context for grasping the complexities of current climate change. The cyclical nature of ice ages reveals that Earth's climate system is inherently sensitive to a range of interconnected factors, many of which continue to operate today. By studying the mechanisms that triggered and terminated these glacial periods, scientists can better interpret ongoing climate variability and anticipate future trends. For instance, the dramatic shifts in global temperatures and ice cover during ice ages highlight the potential for rapid climate transitions, emphasizing that current warming is part of a broader dynamic system rather than an isolated anomaly. Insights gleaned from Ice Age research underscore the importance of feedback mechanisms in climate regulation. During glacial periods, increased ice and snow reflect more sunlight, reinforcing cooling, a process known as albedo feedback. Conversely, during interglacial periods, reduced ice cover leads to more absorption of solar energy, amplifying warming. Recognizing how these feedbacks operate in Earth's history helps scientists predict how current changes, driven by greenhouse gas emissions, may trigger similar or contrasting responses. It also illuminates the delicate balance maintained by Earth's climate system and how delicate shifts can produce profound effects. Furthermore, understanding the natural variability inherent in ice age cycles enhances our ability to distinguish between anthropogenic influences and natural climate fluctuations. This distinction is crucial for developing effective policies and mitigation strategies. Since ice ages are governed by complex interactions between Earth's orbit, solar radiation, atmospheric composition, and ocean currents, analysing their triggers and transitions offers a framework for recognising early signs of climate tipping points today. In essence, the study of ice ages acts as a mirror reflecting Earth's climate resilience and vulnerabilities. It allows us to appreciate the magnitude of natural climate variability and underscores the importance of responsible stewardship of our planet. As we continue to navigate an era of rapid climate change, lessons from Earth's frozen past become invaluable guides, reminding us that climate systems are both remarkably dynamic and profoundly interconnected. Earth's climate history is deeply intertwined with the rhythms of the cosmos. The most influential drivers of long-term climate shifts are astronomical factors that subtly but persistently alter the planet's position relative to the Sun. These celestial influences are primarily governed by three key parameters: the eccentricity of Earth's orbit, the tilt or obliquity of its axis, and the precession of the equinoxes. Together, these elements form what are known as Milankovich cycles, which operate on timescales ranging from tens of thousands to hundreds of thousands of years. Eccentricity describes how elongated Earth's orbit is around the Sun. When the orbit is more elliptical, the distance between Earth and the Sun varies significantly over the year, affecting the intensity of solar radiation Earth receives. These fluctuations influence the seasonal contrasts that are critical in initiating glacial and interglacial periods. While eccentricity changes are relatively slow, occurring over about 100,000-year cycles, their impact on climate can be profound when combined with other orbital variations. The tilt of Earth's axis, or obliquity, varies between approximately 22.1 and 24.5 degrees over roughly 41,000 years. Changes in axial tilt affect the severity of seasons. Greater tilt angles amplify seasonal differences, potentially leading to more extensive ice sheet growth during colder periods. Conversely, a reduced tilt tends to moderate seasons, encouraging the melting of ice and the warming of the planet. Precession, the gradual wobble of Earth's rotational axis, occurs over approximately 26,000 years. This wobble shifts the timing of the seasons relative to Earth's position in its orbit, influencing the distribution of solar energy across hemispheres. When combined with eccentricity and obliquity, precession can either reinforce or diminish seasonal contrasts, thereby playing a crucial role in the cycle of ice ages. These interconnected orbital variations do not operate in isolation. Instead, their cyclical interplay modulates solar insolation, solar energy reaching Earth's surface, over vast timescales. It is this intricate dance of celestial mechanics that underpins the timing and intensity of ice ages, setting the stage for Earth's grand climate rhythms. Understanding these cycles reveals how astronomical factors serve as the slow, persistent puppeteers of our planet's climatic destiny. Milankovich cycles serve as the fundamental rhythm driving Earth's long-term climate variability, orchestrating the timing of ice age cycles through subtle shifts in the planet's orbital parameters. These cycles involve alterations in Earth's eccentricity, axial tilt, and precession, each operating on distinct timescales, ranging from approximately 41,000 to 100,000 years, and collectively modulating the distribution and intensity of solar radiation received at different latitudes and seasons. Eccentricity, the shape of Earth's orbit around the Sun, varies from more circular to more elliptical, influencing the overall amount of solar energy Earth receives. When the orbit becomes more elongated, the difference in solar insolation between perihelion and aphelion intensifies, accentuating seasonal contrasts, especially at high latitudes. Axial tilt, which varies between about 22.1 deg and 24.5 deg, determines the severity of seasons. A larger tilt amplifies seasonal differences, leading to hotter summers and colder winters, while a smaller tilt tends to produce more moderate conditions. Precession, the wobble in Earth's rotational axis, affects the timing of solstices and equinoxes relative to Earth's orbit, altering seasonal contrasts in different hemispheres. The interplay of these cycles creates a complex pattern of climate variability over tens of thousands to hundreds of thousands of years, when the combined effects of eccentricity, tilt, and precession align to produce reduced summer insolation at high northern latitudes. Particularly during the boreal summer, ice sheets can advance, initiating glaciations. Conversely, periods when insolation increases during summers lead to the melting of ice sheets, signaling the end of glacial periods. These orbital variations alone, however, are not the sole architects of ice ages. They set the stage by modulating the amount of solar energy reaching Earth's surface, but other feedback mechanisms, such as changes in atmospheric composition, play critical roles in amplifying or damping the climate response. This intricate dance of orbital mechanics and atmospheric factors underpins the cyclical nature of Earth's ice ages, setting the stage for an exploration of how greenhouse gases influence the rise and fall of these colossal ice sheets. Greenhouse gases, primarily carbon dioxide (CO2) and methane (CH4), serve as key regulators within Earth's climate system, exerting a profound influence on the onset and termination of ice ages. Their role extends beyond mere passive indicators of climatic shifts, actively participating in feedback mechanisms that amplify or mitigate temperature changes. During glacial periods, global temperatures decline and large ice sheets expand, but the extent and persistence of these cold phases are intricately linked to the concentration of greenhouse gases in the atmosphere. As ice sheets grow, they enhance Earth's albedo, reflecting more solar radiation and promoting cooling. Simultaneously, colder temperatures often lead to decreased CO2 levels, since colder oceans absorb less CO2 and biological productivity shifts, reducing greenhouse gas concentrations further. This creates a reinforcing loop that sustains glacial conditions. Conversely, the end of an ice age hinges on the gradual accumulation of greenhouse gases, which trap outgoing infrared radiation more effectively, gradually warming the planet and triggering the retreat of ice sheets. These natural fluctuations in greenhouse gas levels are influenced by a combination of physical, biological and geological processes, including changes in ocean circulation, vegetation cover, and volcanic activity. The interplay between these factors determines how quickly Earth transitions from glacial to interglacial phases. It is crucial to recognize that while orbital variations primarily set the stage for ice age cycles, greenhouse gases act as the amplifiers that determine the severity and duration of these periods. Their concentration in the atmosphere can either reinforce the cooling trend or hasten the warming phase, effectively acting as the climate system's internal modulators. This dynamic underscores the importance of greenhouse gases not only historically, but also in contemporary climate change discussions, as human activities now alter their natural balance, with significant implications for future climate stability. Building on this understanding, it becomes essential to explore other natural phenomena that influence Earth's climate during these cycles, such as volcanic activity and aerosols, which can temporarily disrupt or reinforce the climatic trends driven by greenhouse gases. Volcanic activity and aerosols play a pivotal role in shaping Earth's climate during ice age cycles by influencing the planet's energy balance and atmospheric composition. When volcanoes erupt, they release vast quantities of ash, sulfur dioxide, and other particulates into the stratosphere. These aerosols have a reflective property, scattering incoming solar radiation and temporarily reducing the amount of sunlight reaching Earth's surface. This phenomenon, known as volcanic cooling, can induce short-term climate dips, potentially triggering or intensifying glacial conditions if eruptions occur during sensitive periods of Earth's climate cycle. The impact of aerosols extends beyond immediate cooling. Sulfate aerosols, in particular, can linger in the atmosphere for months or even years, maintaining a reflective layer that sustains lower global temperatures. During ice age transitions, increased volcanic activity can contribute to prolonged cooling phases, reinforcing the buildup of snow and ice by decreasing the warmth that normally prevents glacial expansion. Conversely, the cessation of major eruptions can lead to a gradual reduction in aerosol concentrations, allowing the climate to warm again and potentially end glacial periods. The influence of volcanic aerosols is not isolated. It interacts intricately with other climate drivers such as greenhouse gases and orbital variations. For instance, periods of intensified volcanic activity often coincide with Earth's natural cycles of cooling, amplifying the effects of reduced insolation due to orbital configurations. This synergy can accelerate the initiation of glacial periods, emphasizing the complex feedback mechanisms that govern Earth's climate system. Understanding the role of volcanic aerosols in ice age dynamics underscores the importance of transient external factors in shaping long-term climate patterns. While orbital and atmospheric composition changes set the stage, episodic volcanic events can act as catalysts, tipping the climate toward glacial or interglacial states. Recognizing these interactions deepens our appreciation of Earth's climate complexity and the delicate balance maintained over millennia. As we delve further into the mechanisms behind ice age cycles, it becomes evident that ocean currents and heat distribution are equally vital in modulating the planet's climatic rhythms. Their influence on regional and global temperature patterns offers a compelling chapter in the story of Earth's icy epochs. These vast conveyor-like flows redistribute heat across the globe, with surface currents transporting warm waters from equatorial regions toward higher latitudes, while deep ocean currents carry colder waters toward the equator. This intricate dance of heat movement influences regional climates, often tipping the balance between glaciation and interglacial periods. During ice ages, alterations in ocean current pathways can significantly enhance cooling in polar regions. For instance, shifts in the strength or direction of major currents such as the Gulf Stream or the thermohaline in circulation can limit the amount of warm water reaching higher latitudes. A weakened or disrupted thermohaline system reduces heat transfer to the poles, intensifying ice sheet growth. Conversely, changes that facilitate greater heat influx can mitigate glaciation, temporarily halting or slowing ice age progression. The distribution of heat via ocean currents is intricately linked to the configuration of continents and seafloors. During ice ages, lowered sea levels expose continental shelves and alter current pathways, often reinforcing cooling patterns. These modifications can create feedback loops. For example, expanding ice sheets increase the Earth's albedo, reflecting more sunlight and promoting further cooling. This cooling can strengthen polar sea ice, which acts as an insulator, preventing heat exchange between the ocean and atmosphere, thus perpetuating the cold conditions. In addition, the cooling of the ocean surface during ice ages affects the atmosphere's moisture content, leading to shifts in precipitation patterns that can either promote ice sheet growth or promote regional warming through cloud cover. The complex interplay between ocean currents and heat distribution underscores their vital role in initiating and sustaining glacial cycles. Small variations in these oceanic pathways, driven by tectonic or orbital changes, can cascade into significant climate transformations, setting the stage for the ebb and flow of ice ages. The influence of ocean currents extends beyond mere heat transport. They also set the stage for feedback mechanisms that either amplify or dampen climate fluctuations during these glacial periods. Feedback mechanisms play a crucial role in shaping the intensity and duration of climate fluctuations during ice ages, functioning as either amplifiers or dampers of initial changes. These processes operate through complex interactions within Earth's climate system, often creating feedback loops that reinforce or moderate temperature shifts. A primary amplifier involves the albedo effect, where the expansion of ice sheets increases Earth's reflectivity, or albedo, reducing the absorption of solar energy. As ice sheets grow, they reflect more sunlight, leading to further cooling and additional ice accumulation. Conversely, when ice melts, darker land or ocean surfaces are exposed, absorbing more heat and promoting warming. This negative feedback gradually counteracts rapid temperature declines. Atmospheric greenhouse gases, especially carbon dioxide and methane, serve as pivotal moderators within these feedback systems. During cooler periods, decreased temperatures can lead to the sequestration of greenhouse gases in ice sheets and ocean sediments, reducing their atmospheric concentrations and reinforcing cooling trends. Conversely, warming phases often trigger the release of these gases from natural reservoirs, intensifying the greenhouse effect and accelerating temperature rises. Such dynamic exchanges create a delicate balance, influencing both the onset and retreat of glacial periods. Vegetation cover also participates in climate feedbacks, with expanding ice sheets diminishing land-based plant life, which in turn diminishes carbon sequestration capacity. The reduction in vegetation cover reduces the removal of CO2 from the atmosphere, further amplifying cooling. On the other hand, as glaciers retreat, increased vegetation growth can draw down atmospheric CO2, moderating warming. Oceanic feedback mechanisms, such as changes in thermohaline circulation, influence the distribution of heat and carbon within the climate system. During ice ages, alterations in ocean currents can either reinforce cooling by redistributing cold, deep waters, or temper it by enhancing heat transport from equatorial regions. These complex feedbacks collectively orchestrate the ebb and flow of Earth's glacial cycles, demonstrating how interconnected processes either amplify or dampen climate variations over millennia. Understanding these mechanisms provides vital insights into the intricate dance of Earth's climate system during some of its most extreme episodes. The arrangement of Earth's continents and landmass configurations plays a pivotal role in shaping the planet's climate cycles, particularly during ice ages. Over geological time, shifts in continental positions, driven by plate tectonics, alter oceanic and atmospheric circulation patterns, which in turn influence global climate stability. When continents are situated near the poles, they can promote the development and persistence of ice sheets by providing extensive land-based surfaces suitable for snow accumulation, as seen during past glacial periods. Conversely, when continents are positioned closer to the equator, these regions tend to foster warmer, more tropical climates, reducing the likelihood of ice sheet formation. The configuration of land masses also affects ocean currents, which are crucial in redistributing heat across the globe. For example, the opening or closing of ocean gateways, such as the connection between the Atlantic and Pacific, can dramatically shift heat transport pathways. During certain ice ages, the formation of large land-based barriers like the Isthmus of Panama redirected ocean currents, intensifying cold water flow into northern latitudes and fostering colder conditions that help sustain ice sheets. Additionally, the presence of large land masses in high latitudes can influence atmospheric circulation patterns by modifying the jet streams and storm tracks. These changes can promote extended periods of colder weather over continents, contributing to the advance of glaciers. The configuration of continents also determines the distribution of land and sea, impacting the planet's albedo, its reflectivity. Extensive ice cover over polar landmasses increases Earth's reflectivity, reducing heat absorption and reinforcing cooling trends. Throughout Earth's history, the shifting positions of continents have periodically aligned with orbital variations to produce the cyclical nature of ice ages. As land masses moved, they altered pathways for heat and moisture, setting the stage for the waxing and waning of ice sheets. These large-scale tectonic rearrangements have, over millions of years, interacted with other climatic factors, creating complex feedback mechanisms that drive Earth's long-term climate oscillations. This intricate dance of continents and ocean currents underscores the profound influence landmass configurations exert on Earth's climate system. As we explore further, questions arise. Could external extraterrestrial factors also exert a significant impact on these natural cycles, potentially triggering ice ages? Beyond the forces operating within Earth's atmosphere and oceans, external extraterrestrial factors have long been recognized as influential players in shaping the planet's climate over geological timescales. Among these, variations in the Earth's orbital parameters, collectively known as Milankovich cycles, stand out as primary drivers of long-term climate change, including the onset and retreat of ice ages. These cycles involve subtle changes in the shape of Earth's orbit, eccentricity, the tilt of its axis, obliquity, and the wobble of its rotational axis, precession. Each of these shifts modifies the distribution and intensity of solar radiation, reaching different parts of the planet, gradually nudging Earth's climate toward colder or warmer states. The eccentricity of Earth's orbit fluctuates on cycles of roughly 100,000 and 400,000 years, altering the distance between Earth and the Sun. When the orbit becomes more elliptical, the contrast between seasons intensifies, often promoting cooler summers in the northern hemisphere, conditions conducive to ice sheet expansion. Variations in axial tilt influence the severity of seasons, with a greater tilt amplifying seasonal differences and a smaller tilt promoting more uniform temperatures. Precession, or the wobble of Earth's axis, determines the timing of seasons relative to Earth's position in its orbit, further modulating seasonal climate patterns. These orbital variations do not operate in isolation. Their combined effects influence the amount of solar energy that reaches Earth's surface, especially at high latitudes where ice sheets are most sensitive. During periods when these parameters align to reduce summer insolation in the northern hemisphere, snow and ice tend to persist year-round, gradually accumulating into glaciers. Over thousands of years, this accumulation can expand into vast ice sheets that cover significant portions of the continents, ushering in an ice age. The interplay of cosmic influences with Earth's internal climate systems underscores the complexity of ice age cycles. Recognizing the role of extraterrestrial factors enriches our understanding of how external forces can tip the delicate balance of Earth's climate, setting the stage for the dramatic glacial episodes that have punctuated our planet's history. With this foundation, we turn to explore what glaciers are and how they form during these icy epochs. Glaciers are among the most striking natural features of the Ice Age landscape, embodying the immense power of accumulated ice over time. They are vast, slow-moving rivers of ice that originate from compacted snow, gradually transforming into dense, crystalline ice under relentless pressure. Unlike seasonal snowfalls, glaciers are formed through a prolonged process where snowfall exceeds melting and sublimation over many years, leading to persistent buildup. This accumulation begins in areas where the climate remains cold enough to prevent complete melting, typically at higher latitudes or elevations. As snow layers thicken, the weight compresses the lower strata, expelling air pockets and increasing density. Over decades or even centuries, these layers meld into solid ice. The transformation is not instantaneous, but a gradual transition driven by the combined effects of gravity, pressure, and temperature. Once a critical mass is reached, the ice begins to flow slowly outward and downhill, carving valleys and shaping the terrain beneath them. The process of glacier formation is intricately linked to the climate conditions of the Ice Age. Cooler global temperatures meant that snow persisted longer each year, allowing glaciers to grow larger and more extensive. As snowfall continued unabated, glaciers expanded both in thickness and lateral extent, often merging into larger ice masses. These burgeoning glaciers could cover vast areas, sometimes spanning hundreds of thousands of square kilometers. The dynamics of glacier growth involve a delicate balance between accumulation at the surface and melting or sublimation at the edges. When accumulation surpasses loss, the glacier advances, pushing forward into new territory. Conversely, if melting outpaces snowfall, the glacier retreats. During ice ages, prolonged periods of cold climate tipped this balance in favor of growth, leading to the formation of enormous ice sheets that blanketed large portions of continents. Understanding how glaciers form during these frigid epochs illuminates the processes behind their growth and movement. It also sets the stage for examining the larger-scale phenomena, how these ice masses evolve into the formidable ice sheets like the Laurentide and Eurasian sheets, which dramatically reshaped Earth's surface during the Ice Age. The growth and expansion of large ice sheets such as the Laurentide and Eurasian sheets are driven by a complex interplay of climatic, topographical, and oceanic factors. During periods of significant cooling, typically associated with glacial maxima, increased snowfall begins to accumulate over vast land areas. This accumulation surpasses the amount of ice melting during warmer seasons, leading to a net gain in ice mass. Over time, this persistent build-up causes the ice sheet to extend outward, filling valleys and covering extensive portions of the continent. The development of an ice sheet involves a delicate balance between accumulation and ablation. Snowfall, often driven by colder temperatures and increased moisture availability from polar or westerly winds, deposits layers of snow that gradually compress into dense ice due to pressure from overlying layers. This process, called fernification, transforms granular snow into solid ice over decades or centuries. As the ice thickens, basal pressure increases, causing the ice to flow outward under its own weight, shaped by the underlying topography. Gravity acts as a key driver, enabling the ice to slide and deform, slowly carving through landscapes and extending the ice's reach. Climate fluctuations play a pivotal role in the expansion phases. Cooler periods, like ice ages, see global temperatures drop, reducing melting rates significantly. Additionally, changes in sea levels and ocean currents can influence the amount of moisture delivered to the ice sheet margins, fueling further growth. The size of these sheets also depends on the availability of moisture sources, the topography of the land, and the presence of ice-dividing mountain ranges that can funnel snowfall into specific regions. The Laurentide ice sheet, for example, expanded dramatically during the last glacial period, covering much of North America, driven by a combination of lowered temperatures and increased snowfall in northern latitudes. Similarly, the Eurasian ice sheet grew through extensive snowfall across northern Europe and Siberia, reinforced by cold Arctic air masses. This process of build-up and expansion is a testament to the dynamic interactions between climate, geography, and atmospheric circulation. As these vast ice sheets grew, they not only shaped the Earth's surface but also profoundly influenced global climate patterns and sea levels during the Ice Age era. Building from this understanding, it is essential to distinguish the different forms of ice masses. How do ice sheets differ from ice caps and glaciers? While glaciers, ice caps, and ice sheets are all immense accumulations of ice, each differs notably in size, location, and influence on the landscape. These distinctions are fundamental to understanding how they shape the Earth's surface in unique ways. Ice sheets are the largest of the three, sprawling over thousands of square kilometers and containing vast quantities of ice, primarily found in Greenland and Antarctica. These colossal masses extend beyond the boundaries of land, often covering entire continental regions, and are capable of reshaping entire landscapes through their immense weight and movement. Their sheer scale means they can influence global sea levels and climate patterns, making them critical players in Earth's climate system. In contrast, ice caps are smaller, though still sizable, typically covering high altitude or polar regions. They are dome-shaped masses that blanket mountainous terrain or polar islands, usually spanning less than 50,000 square kilometers. Unlike ice sheets, ice caps are more localized, shaping the immediate landscape beneath them, but lacking the capacity to influence vast continental areas. Glaciers, on the other hand, are more dynamic and varied in size, from tiny mountain glaciers to expansive valley glaciers. They often originate from ice caps and ice sheets, flowing slowly down valleys or across rugged terrains. Their mobility is driven by gravity, allowing them to carve out valleys, fjords, and other features over time. Because glaciers are more mobile and often situated within specific regions, their erosive and depositional activities directly sculpt the terrain beneath and around them. Understanding these distinctions lays the foundation for exploring how glaciers actively modify landscapes. Their movement, driven by gravity and temperature fluctuations, results in powerful erosive forces that carve valleys and transport debris. Simultaneously, as they melt, they deposit sediment and reshape the terrain, creating features like moraines and outwash plains. This dynamic interplay of erosion and deposition is central to the transformative role glaciers have played throughout Earth's history. Glaciers are formidable agents of landscape transformation, their immense weight and persistent movement carving out the topography we observe today. As they traverse the terrain, glaciers act both as sculptors and depositors, reshaping the land through a dynamic interplay of erosion and deposition. This dual role is central to understanding how glaciers influence Earth's surface features. Erosion by glaciers primarily occurs through processes such as plucking and abrasion. Plucking involves the glacier loosening blocks of bedrock as meltwater penetrates cracks and refreezes, effectively lifting these fragments from the underlying surface. This action leaves behind jagged, rough terrains and contributes to the formation of distinctive landforms like roches moutonnées, smooth, rounded hills on one side with steep, jagged edges on the other. Abrasion complements this by grinding against bedrock with embedded debris and rock flour, finely ground rock particles produced by the glacier's abrasive action, creating smooth striations and polished surfaces. These features serve as persistent records of glacier movement, revealing the direction and intensity of past flows. Deposition, on the other hand, occurs when glaciers lose energy, causing transported material to settle and accumulate. As glaciers advance or retreat, they deposit a variety of sediments, ranging from fine silt to large boulders. Moraines, accumulations of debris along the sides, lateral moraines, at the terminus, terminal moraines, or within the glacier, medial moraines, are prominent features resulting from this process. These deposits not only mark the glacier's past extent, but also influence subsequent landscape evolution, creating fertile grounds and distinct landform boundaries. The interplay of erosion and deposition by glaciers leads to a diverse array of geomorphological features, U-shaped valleys, fjords, and drumlins, each bearing the signature of glacial activity. The relentless advance and retreat of glaciers sculpt the land incrementally, their erosive power unveiling bedrock and depositing sediments that shape the terrain long after the ice has melted away. Understanding these processes illuminates how glaciers have continuously molded Earth's surface, leaving behind a landscape rich in history and geological complexity. Building upon this foundation of glacial impact, it becomes essential to explore the mechanisms that govern how glaciers move and flow, enabling these powerful erosional and depositional processes to occur. The movement and flow of glaciers are driven by a complex interplay of physical processes that allow immense masses of ice to traverse vast distances over time. At the core of this movement is the phenomenon of plastic deformation, where the ice's internal structure gradually distorts under pressure. As the weight of accumulated snow compresses the underlying layers, the ice becomes semi-fluid, allowing it to slowly deform and flow. This process is most prominent in the deeper, warmer parts of the glacier, where the temperature and pressure facilitate such deformation. Surface melting also plays a significant role in glacier dynamics. When meltwater forms on the glacier's surface, it can percolate through crevasses and moulins, reaching the base and lubricating the interface between the ice and its bedrock. This lubrication reduces friction, enabling the glacier to slide more readily over its substrate. Such basal sliding is often responsible for rapid advances or surges in glacier movement, especially in temperate glaciers where melting is more prevalent. In addition to internal deformation and basal sliding, the glacier's shape and the underlying topography influence its flow patterns. Steep slopes can accelerate movement, while bedrock irregularities can cause zones of compression or extension within the ice. As glaciers encounter obstacles or changes in terrain, they often develop crevasses, which are not only surface features but also indicators of stress within the ice mass. These features reflect the dynamic response of glaciers to underlying forces and external influences. The flow of glaciers is further affected by climatic conditions that influence accumulation and ablation rates, thus controlling the overall mass balance. Variations in temperature, snowfall, and meltwater production can alter the speed and direction of glacier movement over time. The intricate balance of internal deformation, basal sliding, and external forces creates the dynamic, ever-changing nature of glaciers, true giants shaped by both their internal physics and external environment. Building on this understanding of glacier mechanics, it becomes crucial to explore how scientists quantify and reconstruct the size and volume of ancient ice sheets, offering insights into Earth's climatic past. Determining the size and volume of ancient ice sheets requires a combination of innovative measurement techniques and sophisticated modelling approaches, rooted in both direct observations and indirect geological evidence. Since direct measurement is impossible for prehistoric periods, scientists rely on a suite of methods that reconstruct past ice sheet configurations with remarkable precision. One primary approach involves the analysis of landforms shaped by glacial activity, such as U-shaped valleys, fjords, and drumlins, which serve as tangible records of past ice cover. These features reveal the extent of ice sheets and help delineate their boundaries during different periods. Sediment deposits also provide critical clues. For example, glacial till, unsorted sediments deposited directly by ice, indicate zones of former ice presence, while stratified sediments can reveal fluctuations in ice extent over time. Isotopic analysis of marine and lacustrine sediments further refines these reconstructions. For instance, oxygen isotope ratios in deep-sea cores serve as proxies for global ice volume, with lighter isotopes becoming more prevalent in ocean water during glacial periods as ice sheets draw water from the oceans. These isotopic signatures, combined with data from ice-rafted debris, help estimate the volume of ice stored on land. Advances in geophysical techniques, such as seismic surveys and gravity measurements, allow scientists to infer the thickness and internal structure of remaining ice sheets, and to model the past extent of larger ice sheets by extrapolating these data. Computer models integrate these diverse data sources, simulating ice sheet growth and decay over time by accounting for climate variables, topography, and bedrock interactions. These models, calibrated against geological evidence, enable researchers to generate detailed reconstructions of ice sheet evolution, providing estimates of their total volume and influence on global sea levels. Through this multidisciplinary approach, combining landform analysis, sedimentology, isotopic studies, and numerical modelling, scientists piece together the dynamic history of Earth's ice sheets. This ongoing synthesis deepens our understanding of how these icy giants waxed and waned through the ages, shaping the planet's climate and landscapes long before recorded history. the remnants of past glaciers and ice sheets are etched into the Earth's geological record, providing crucial insights into their historical extents and dynamics. One of the most compelling forms of evidence is the presence of striations, long linear scratches carved into bedrock by the relentless movement of glacial ice. These deep grooves reveal not only the direction of ice flow, but also attest to the immense pressure exerted over millennia. Often, these striations are accompanied by polished surfaces that reflect the abrasive power of glacial debris embedded within the ice. In addition to surface markings, scientists identify distinctive landforms shaped by glacial activity. Moraines, ridges composed of unsorted till deposited at the edges of glaciers, mark former ice boundaries. Terminal moraines, for instance, serve as markers of the furthest advance of a glacier during its maximum extension. Similarly, lateral moraines form alongside the sides of glaciers, outlining their past margins. These features, sometimes spanning hundreds of kilometers, provide a tangible record of ice sheet fluctuations. Subglacial lakes and sediments also contribute vital clues. When glaciers melt or retreat, they leave behind layers of fine-grained sediments known as varves, annual deposits of silt and clay that preserve seasonal variations. Counting these varves enables scientists to reconstruct changes in ice sheet size over thousands of years. Moreover, the presence of drop stones, large stones transported by ice and dropped into finer sediments, indicates the movement of icebergs carving from ice sheets into oceans. Ice-rufted debris found in marine sediments further corroborates the extent of glacial coverage. When ice sheets carve icebergs, they carry rocky material that eventually melts and sinks, leaving a trail of debris across ocean floors. Analysing these deposits helps chart the timeline of glacial retreats and advances. Combining these diverse lines of evidence, bedrock markings, landforms, sediments, and debris, paints a detailed picture of how glaciers and ice sheets waxed and waned through Earth's climatic history, revealing the dynamic nature of ice during the ice ages. Ice sheets, vast expanses of glacial ice covering significant portions of continents, serve as powerful agents in shaping global sea levels during ice age periods. When these colossal masses of ice accumulate, they lock away enormous volumes of fresh water, effectively reducing the amount of water available in the oceans. This sequestration results in a notable drop in sea levels, often by as much as 120 meters, around 394 feet, compared to current levels during peak glaciations. Such dramatic drops expose continental shelves and create land bridges that dramatically alter coastal landscapes and migration pathways for both humans and animals. Conversely, when the climate warms and the ice age wanes, these glaciers and ice sheets melt back, releasing their stored water into the oceans. This process causes sea levels to rise, sometimes rapidly, flooding low-lying coastal regions and reshaping the planet's geography. The ebb and flow of these ice masses are driven by complex interactions between atmospheric temperatures, ocean currents, and Earth's orbital variations, creating a dynamic cycle of glaciation and deglaciation that has punctuated Earth's history. The scale of these changes underscores the profound influence ice sheets exert on global climate systems. Their expansion cools the planet further by reflecting sunlight through their reflective surfaces, while their retreat accelerates warming by allowing more solar energy to reach the ocean and land surfaces. These feedback mechanisms demonstrate the delicate balance maintained within Earth's climate system and highlight the sensitivity of sea levels to the growth or melting of ice sheets. Understanding the relationship between ice sheets and sea levels illuminates the broader story of Earth's climatic shifts. It reveals how natural processes have continually reshaped the world's geography, affecting sea routes, ecosystems, and human civilizations alike. As scientists study past glacial cycles, they gain valuable insights into potential future changes driven by ongoing climate variations. This knowledge not only deepens our appreciation for Earth's dynamic history, but also emphasizes the importance of monitoring current ice sheet behavior, given its direct impact on sea level stability and global climate health. Building from these insights, it is natural to wonder, what types of plants manage to survive and even thrive during these cold, challenging ice age conditions, and how did they adapt to such extreme environments? During the icy epochs of the Ice Age, plant life faced extreme challenges that demanded remarkable adaptations for survival. While much attention is often given to the megafauna that roamed these frozen landscapes, the resilient flora played a crucial role in sustaining ecosystems. Tundra and steppe vegetation dominated these cold environments, characterized by hardy, low-growing plants that minimized exposure to biting winds and freezing temperatures. Among these were mosses, lichens, dwarf shrubs, and grasses, all of which exhibited unique adaptations to thrive in such harsh conditions. Lichens, a symbiotic partnership between fungi and algae, are particularly notable for their resilience. They can endure prolonged periods of desiccation and extreme cold, often surviving on bare rock surfaces where other plants could not establish. Their ability to photosynthesize at low temperatures allowed them to serve as a vital early colonizer in barren landscapes. Dwarf shrubs, such as Arctic willow and crowberry, developed compact low-lying forms that reduced wind resistance and conserved heat. These plants often had small, thick leaves with waxy coatings to minimize water loss, a critical adaptation given the limited liquid water availability beneath the ice sheets. Grasses and sedges, with their extensive root systems, could quickly sprout when conditions allowed, taking advantage of the brief warm spells in the glacial cycles. Their growth habits and reproductive strategies, such as producing seeds capable of dispersing over long distances, helped them colonize new areas rapidly. Many of these plants also entered dormant phases during the coldest periods, resuming growth when temperatures rose. Such physiological flexibility was essential for surviving the extreme seasonal variations characteristic of Ice Age climates. These plant adaptations not only ensured their survival, but also laid the groundwork for subsequent ecological succession. Their persistence created microhabitats that supported insects, small mammals, and eventually larger animals. In the icy wilderness, life persisted, cloaked in resilience and ingenuity, adapting to one of Earth's most formidable climates. Building on the story of survival, it's natural to wonder which animal species managed to endure these frigid conditions, and how they adapted to the relentless cold. During the Ice Age, certain animal species rose to dominance by evolving remarkable adaptations that allowed them to withstand the extreme cold, scarce resources, and changing landscapes. These megafauna not only shaped their ecosystems, but also exemplified resilience through specialized physical features and behaviors tailored for survival in icy environments. Mammoths, perhaps the most iconic Ice Age inhabitants, possessed thick, layered fur that provided insulation against frigid temperatures. Their expansive, curved tusks served multiple functions, from foraging beneath snow to defense against predators. Their large size, a phenomenon known as Bergmann's rule, helped conserve heat by reducing surface area relative to volume. Additionally, mammoths had a heightened ability to dig through snow and ice to access grasses, shrubs, and other vegetation buried beneath the frozen surface, demonstrating their adaptability to seasonal scarcity. Similarly, saber-toothed cats, with their formidable elongated canines, were apex predators optimized for hunting large herbivores. Their muscular builds and short, powerful limbs allowed for explosive bursts of speed, crucial for ambushing prey in open tundra landscapes. Their robust jaws and wide skulls facilitated powerful bites, while their sharp teeth were specialized for slicing flesh, making them effective hunters despite the challenging environment. Some evidence suggests they might have had thick fur or other insulating features, enhancing their ability to survive in colder regions. Giant ground sloths, including species like Megatherium, adapted to a life of slow, deliberate movement in open plains and woodlands. Their massive bodies were covered with coarse fur, and their large curved claws helped them access foliage from tall trees and shrubs. Their low metabolic rate and immense size also contributed to heat retention, enabling them to endure colder climates. Their herbivorous diet relied on browsing available vegetation, even during harsh winters, with their size serving as an advantage in conserving warmth. Together, these species exemplify the extraordinary adaptations that allowed Ice Age megafauna to flourish amid environmental challenges. Their physical and behavioral traits reflect a delicate balance of specialization and resilience, enabling survival in an era defined by relentless cold and ecological upheaval. This resilience raises a compelling question. How did other megafauna, like mammoths, saber-toothed cats, and giant sloths, managed to endure the extreme climates of the Ice Age. The survival strategies of Ice Age megafauna such as mammoths, saber-toothed cats, and giant sloths reveal remarkable adaptations to the frigid environments they inhabited. These creatures evolved features that enabled them to endure the extreme cold and scarce resources characteristic of glacial periods. Thick, insulating layers of fat and dense fur provided essential warmth, creating a barrier against the biting wind and low temperatures. Mammoths, for instance, boasted a thick, woolly coat and a substantial fat layer that served both as insulation and energy reserves during long, harsh winters. Beyond physical adaptations, behavioral strategies played a crucial role. Many of these animals migrated seasonally, following herds to areas with more abundant food supplies, thus avoiding the most severe conditions. Their social structures also contributed to survival, with herd behaviors offering protection against predators and facilitating cooperative care of young and injured individuals. Saber-toothed cats, despite their predatory nature, likely relied on ambush tactics and dense vegetation to hunt effectively, while giant sloths used their powerful limbs to browse on the hardy, browse-rich plants that remained available even under snow cover. Dietary flexibility was another vital aspect of their resilience. Many megafauna species could consume a variety of plant matter, including twigs, shrubs, and roots, which were accessible during winter months when grasses were scarce. Their digestive systems evolved to maximize nutrient extraction from these less-than-ideal food sources, enabling them to sustain themselves through the most challenging times. Additionally, some species possessed specialized morphological features that directly addressed environmental challenges. For example, mammoths had large, curved tusks that could be used to dig through snow and ice to access buried vegetation. Their sturdy limb bones and broad feet prevented sinking into snow, facilitating movement across icy terrain. The remarkable adaptations of these megafauna reflect a complex interplay of physical features, behaviors, and ecological strategies that allowed them to survive in some of the Earth's coldest regions during the Ice Age. Their resilience underscores the extraordinary versatility of life in the face of extreme climatic adversity, setting the stage for understanding how we uncover evidence of these ancient ecosystems today. Fossilized bones, preserved remains, and a variety of other geological clues form the backbone of our understanding of Ice Age ecosystems. These remnants offer a window into a world long vanished, revealing the diversity of species that once thrived across vast icy landscapes. For instance, large megafauna like mammoths, mastodons, and giant sloths leave behind extensive skeletal remains, often found in permafrost or buried within sediment layers. These fossils not only confirm the existence of these creatures, but also provide insights into their size, diet, and even some aspects of their behavior. Preserved soft tissues such as hair, skin, and even stomach contents have been recovered from remarkably well-preserved specimens. These rare finds allow scientists to analyze ancient DNA, reconstructing genetic lineages and exploring evolutionary relationships between extinct and modern species. For example, DNA extracted from mammoth remains has shed light on their migration patterns and how they adapted to changing climates. Similarly, preserved pollen and plant material embedded within ice cores and sediment layers reveal the types of flora that supported these ecosystems, illustrating how plant communities shifted with glacial advances and retreats. The study of cave paintings and carvings also contributes to our understanding, offering visual representations of animals that roamed during the Ice Age. These artistic depictions, combined with the physical evidence, enable researchers to piece together the complex web of predator-prey relationships and habitat preferences. Isotope analysis of fossilized bones further informs us about the diets of extinct species and their migratory behaviors, revealing how they responded to environmental fluctuations. These diverse lines of evidence collectively reconstruct dynamic ecosystems characterized by a rich interplay between animals, plants, and climate. They highlight not only the biodiversity of Ice Age worlds, but also the profound impacts of climatic shifts on these ancient communities. As we delve deeper into this frozen past, the evidence continues to clarify how intricate and resilient these ecosystems once were, setting the stage for understanding the dramatic changes that led to their eventual disappearance. This naturally leads us to explore how and why so many of these remarkable species went extinct, and the leading hypotheses that attempt to explain this profound loss. The disappearance of numerous Ice Age species remains a subject of intense scientific inquiry, with multiple theories proposed to explain these extinctions. As glaciers advanced and retreated across vast landscapes, environmental conditions fluctuated dramatically, impacting the delicate balance of ecosystems. Many species, once thriving in icy tundras or expansive steppe environments, faced sudden habitat loss, forcing them to either adapt rapidly or perish. The leading explanations for these extinctions often focus on a combination of climate change and human activity. Climate shifts during the end of the Ice Age gradually transformed icy habitats into more temperate zones. For cold-adapted megafauna such as mammoths, mastodons, and giant ground sloths, these changes meant shrinking home ranges and dwindling food sources. As temperatures rose, the grasslands and steppe ecosystems they depended on contracted, pushing species into smaller refugia or isolated pockets. Without quick adaptation or migration, many populations declined and eventually vanished. Evidence suggests that the pace of climate change outstripped their capacity to evolve or relocate, leading to widespread extinctions. The arrival of humans added another layer of complexity. Early humans, armed with increasingly sophisticated tools, explored and exploited new territories. Overhunting likely contributed to the decline of certain species, especially those already stressed by environmental shifts. The rapid spread of human populations into Ice Age habitats coincided with the timing of many extinctions, prompting debates about the extent of human impact versus environmental factors. Some scientists also consider the role of disease and ecological competition, where new predators or competitors introduced by migrating humans or other species further destabilized fragile populations. Additionally, genetic studies indicate that small, isolated populations suffered from inbreeding depression, reducing their resilience to environmental stresses. In sum, the extinction of Ice Age species appears to have resulted from a complex interplay of shifting climates, human pressures, and ecological dynamics. This intricate web of factors underscores the vulnerability of species facing rapid environmental change, a theme that resonates in understanding both past and present biodiversity crises. As we explore the adaptability of life during this period, it leads naturally into how plants and animals responded to these upheavals through migration and evolutionary adaptations. As the Ice Age advanced and retreated, the shifting climate imposed relentless pressures on both plant and animal populations, compelling them to innovate survival strategies. Migration proved to be a primary response. Species moved in search of more hospitable environments, often travelling vast distances across ice sheets, tundra, and forested corridors. For instance, large herbivores such as mammoths and reindeer tracked the oscillating edge of ice sheets, following patches of vegetation that persisted in refugia, small pockets where conditions remained relatively stable. These refugia became crucial sanctuaries, allowing species to survive periods of extreme cold and habitat loss. In addition to migration, many organisms adopted remarkable adaptations to withstand the rigors of a frozen world. Plants, for example, evolved antifreeze proteins that prevented ice crystal formation within their tissues, enabling them to survive in sub-zero temperatures. Some developed specialized growth forms, such as low-growing shrubs and mosses, which minimized exposure to harsh winds and cold stress. Many perennial plants entered dormancy during the coldest months, conserving energy until conditions improved. On the animal side, thickened fur, increased fat deposits, and behavioral adaptations like burrowing or hibernation became widespread among mammals. The woolly mammoth, with its dense coat and fatty hump, epitomized these evolutionary responses aimed at insulation and energy conservation. Furthermore, certain species altered their reproductive timing to coincide with favorable conditions, ensuring offspring had the best chance of survival. Some animals developed seasonal migration patterns that synchronized with the availability of food resources, effectively tracking the shifting ecosystems. This dynamic interplay between migration and adaptation not only facilitated individual survival, but also shaped community structures, influencing predator-prey interactions and the distribution of species across the continent. These survival strategies highlight the remarkable resilience of life in the face of relentless environmental change. As the climate continued to oscillate, plants and animals refined their responses, setting the stage for complex ecological interactions. Understanding how these organisms managed to endure the Ice Age's extreme conditions invites deeper inquiry into how predator-prey relationships evolved amid such profound transformations. During the Ice Age, predator-prey relationships underwent significant transformations driven by the shifting environment and the immense pressures of survival. As glaciers expanded and climates grew harsher, the distribution and abundance of species changed dramatically, forcing both predators and prey to adapt swiftly. Large herbivores, such as mammoths and reindeer, roamed vast icy plains, developing strategies to evade increasingly specialized predators. Conversely, predators like saber-toothed cats and giant wolves evolved formidable adaptations, elongated canines, powerful limbs, and keen senses to exploit these abundant prey populations efficiently. The scarcity of resources in frozen landscapes heightened the stakes of these interactions. Predators often relied on endurance hunting, stalking prey across expansive territories, while prey species developed heightened alertness, herd behaviors, and swift escape responses. The evolution of these relationships was marked by a continuous arms race. Prey species became faster, more alert, and more social, while predators sharpened their hunting tactics and physical tools. For example, some predators specialized in ambushing prey, while others evolved to pursue over long distances, adapting their physiology to the demands of cold, open environments. The dynamic between predator and prey also influenced broader evolutionary patterns. In some cases, the intense selection pressures led to the emergence of highly specialized species, each finely tuned for survival in the icy wilderness. The predator's need for efficient hunting drove morphological innovations, such as the development of heightened sensory organs or increased bite force, while prey species diversified into various forms to exploit different ecological niches or evade predation altogether. This ongoing evolutionary dance contributed to the remarkable biodiversity observed during the Ice Age. The adaptations forged in these predator-prey relationships not only shaped the survival strategies of individual species, but also influenced community structures and ecological balances. As we consider how life persisted and thrived amid the icy extremes, it becomes clear that these interactions were fundamental drivers of evolutionary change, setting the stage for the complex web of life that would emerge once the ice receded. Their legacy extends beyond the Ice Age, laying the groundwork for the intricate evolutionary pathways seen in modern ecosystems. This interconnected history demonstrates how survival in a frozen world was a constant negotiation, balancing the predator's pursuit with the prey's evasive ingenuity, ultimately fueling the relentless march of evolution. The flora and fauna of the Ice Age profoundly influenced the trajectory of Earth's evolutionary history, acting as both architects and catalysts for change across countless species. As glaciers advanced and retreated in rhythmic cycles, ecosystems were repeatedly reshaped, fostering adaptations that would define the survival strategies of many organisms. Cold-tolerant plant species such as mosses, lichens, and hardy grasses thrived in tundra landscapes, establishing resilient habitats that supported diverse herbivores. These plants not only sustained large megafauna, like mammoths, mastodons, and giant deer, but also created complex food webs that intertwined the fate of predator and prey alike. Large herbivores, in turn, played a pivotal role in shaping the environment itself. Their grazing patterns influenced vegetation distribution, helping to maintain open landscapes that favoured certain plant communities over forested regions. The immense size and mobility of these animals enabled them to traverse vast icy expanses, often acting as keystone species that dictated the structure of their ecosystems. Their presence and eventual extinction, driven by climate shifts and human activity, led to significant ecological changes, highlighting the delicate balance within Ice Age environments. The interactions between flora and fauna during this period also spurred evolutionary innovations. For example, the development of thick fur and fat layers in many mammals was a direct response to the harsh, icy conditions, while certain plant species evolved mechanisms for surviving extreme cold and limited sunlight. These adaptations not only ensured survival during the glacial cycles, but also laid the groundwork for future evolutionary pathways. As the Ice Age progressed, shifting climates and the resulting environmental pressures fostered diversification and migration of species. The changing landscape created corridors and barriers, shaping patterns of speciation and extinction. Such dynamic interactions between climate, flora, and fauna ultimately sculpted the biological tapestry we observe today, underscoring their integral role in Earth's evolutionary narrative. Recognizing this interconnected history invites a deeper understanding of how life on our planet continually adapts and transforms in response to planetary rhythms. The frigid landscapes of the Ice Age did more than shape the world's terrain. They profoundly impacted the course of human evolution and migration. As glaciers expanded and retreated in rhythmic cycles, early humans were compelled to adapt swiftly to changing environments. These climatic shifts created a patchwork of habitable zones, often isolated by vast ice sheets and tundra, leading to both diversification and migration of human populations. Cold environments demanded innovative survival strategies. Early humans developed new tools suited for hunting large Ice Age megafauna like mammoths and reindeer, which thrived in these icy conditions. The necessity to access sparse resources fostered technological advancements, including the crafting of specialized weapons and clothing from animal hides. These innovations not only enhanced survival chances, but also contributed to the development of complex social behaviors and cultural practices. Migration patterns during the Ice Age were directly influenced by climate fluctuations. As ice sheets advanced, populations retreated to refugia, areas with more favorable climates, such as southern Europe, the Middle East, and parts of Asia. When warming periods arrived, these groups expanded into new territories, sometimes crossing land bridges like Beringia, which emerged from lowered sea levels. Such migrations led to the widespread dispersal of Homo sapiens and other hominin species across continents, facilitating genetic exchange and cultural diffusion. The harsh climates also exerted evolutionary pressures, selecting for physiological traits suited to cold environments. For instance, populations in northern regions often developed increased body fat and larger limbs, adaptations that enhanced heat retention. Over thousands of years, these adaptations became ingrained, illustrating how climate shaped not only migration routes but also human biology. In essence, the Ice Age's fluctuating climate landscape served as both a barrier and a catalyst for human development. They forced our ancestors to innovate, migrate, and adapt in ways that laid the groundwork for the diversity and resilience characteristic of modern humans. As we explore the evidence of early settlements and activities during this icy epoch, we uncover the story of survival and ingenuity etched into our very origins. Evidence of early human settlements and activities during the Ice Age offers a vivid glimpse into how our ancestors navigated a world transformed by relentless cold and shifting landscapes. Archaeological findings reveal that human groups established semi-permanent campsites in strategic locations, often near abundant resources such as rivers, lakes, or animal migration routes. These sites, identified through remnants like stone tools, hearths, and animal bones, serve as tangible markers of human presence amid the icy wilderness. One of the most compelling pieces of evidence comes from the discovery of shelter structures beneath layers of ice and sediment. In regions like the Paleolithic caves of Europe, such as those in France and Spain, cave paintings depict scenes of hunting and daily life, suggesting not only activity but also symbolic expression and social cohesion. These artworks, some dating back tens of thousands of years, demonstrate that early humans engaged in complex cultural behaviors even in harsh conditions. Further clues emerge from the variety and sophistication of tools unearthed at these sites. Scrapers, blades, and projectile points crafted from stone, bone, and ivory reveal specialized techniques tailored to hunting large Ice Age mammals like mammoths, reindeer, and bison. The presence of tools designed for specific tasks indicates a deep understanding of their environment and resource management. In addition, the discovery of animal remains with cut marks provides direct evidence of butchering practices, offering insights into subsistence strategies. In some regions, evidence of clothing and shelter construction demonstrates adaptive ingenuity. For example, preserved animal hides and bone structures suggest that early humans developed insulating garments and portable dwellings to withstand the cold. These innovations not only facilitated survival, but also fostered social bonds and the transmission of skills across generations. All these archaeological clues, settlement sites, art, tools, and remains collectively paint a picture of resilient communities actively shaping their environment despite the challenges of the Ice Age. They underscore a remarkable capacity for adaptation, laying the groundwork for the next phase of human evolution, physical and cultural strategies that would enable survival in these extreme conditions. As we explore these adaptations, the story of human resilience becomes even more compelling, illustrating a continuous dance between environment and ingenuity. Faced with the relentless chill of the Ice Age, humans exhibited remarkable ingenuity in both their physical adaptations and cultural innovations. Physically, our ancestors evolved traits that enhanced their survival prospects in frigid environments. For instance, a broader body and shorter limbs, traits associated with Bergmann's and Allen's rules, helped conserve heat by reducing surface area relative to volume. A stockier build minimized heat loss, while increased subcutaneous fat provided vital insulation, forming a natural thermal barrier beneath the skin. Additionally, certain populations developed increased nasal cavity size, which may have warmed cold air before reaching the lungs, further aiding in thermoregulation. Beyond anatomy, humans also adapted culturally, developing behaviors that complemented their biological traits. Clothing became an essential aspect of survival, with early humans crafting garments from animal hides and furs. These materials acted as insulation, trapping body heat and shielding against icy winds. The importance of clothing was so significant that it likely influenced social structures, encouraging cooperation in hunting and dressing animals for insulation purposes. Shelter construction also evolved, with humans building semi-permanent dwellings from bones, hides, and earth, designed to retain heat and withstand harsh weather. Fire, meanwhile, became a cornerstone of survival, not only providing warmth, but also enabling cooking, which unlocked nutrient-rich foods and made them easier to digest. Social cooperation played a crucial role as well. Sharing resources, collective hunting strategies, and communal fire-building efforts increased the chances of individual and group survival in cold landscapes. These cultural adaptations also fostered the transmission of survival knowledge across generations, creating a collective resilience against the relentless cold. All these adaptations, biological traits, clothing, shelter, fire use, and social cooperation, formed an integrated survival strategy. They reflect a complex interplay between biology and culture, illustrating how humans not only endured, but thrived amidst the Ice Age's icy grip. As we consider these strategies, it becomes clear that our ancestors' ingenuity extended well beyond mere survival, shaping the foundations of human resilience that continue to influence us today. This natural progression leads us to explore the specific tools and technologies that further enhance their ability to cope with the demanding cold. Ice Age humans demonstrated remarkable ingenuity in developing tools and technologies tailored to withstand the harsh, frigid environment. Facing relentless cold, they crafted specialized implements not only for hunting and gathering, but also for survival in a landscape where warmth and protection were paramount. One of their most significant innovations was the creation of clothing from animal hides and fur, which provided essential insulation. To process these materials effectively, they developed sharp stone blades and scrapers, transforming raw hides into functional garments. These tools evolved over generations, becoming more refined with finer edges for cutting and sewing, allowing humans to fashion layered clothing that minimized heat loss. Shelter building also saw advancements driven by climatic challenges. Early humans constructed temporary dwellings from animal bones, wood, and hides, designed to insulate against the cold. They learned to manipulate natural materials to create insulated hearths and fire pits, which served as both warmth sources and centers for social activity. Fire itself became a crucial tool, not only for warmth but also for cooking food, which improved nutrition and energy intake, vital in a resource-scarce environment. The mastery of fire-making techniques, such as striking flint to produce sparks, marked a significant technological milestone. In addition to clothing and fire, Ice Age humans crafted composite tools that combined stone with bone or antler. These multi-material implements enhanced efficiency in hunting and processing game, which was vital for survival amid limited resources. For example, spear throwers or atlatls increased the range and force of hunting tools, enabling humans to hunt larger game from a safer distance. Their ability to manufacture durable, multifunctional tools demonstrated an understanding of material properties and an adaptive mindset essential for thriving in a cold, unpredictable climate. Collectively, these technological innovations reveal a profound capacity to adapt to the environmental pressures of the Ice Age. They reflect not only a mastery of raw materials, but also an evolving understanding of how to manipulate their surroundings to meet fundamental needs. As humans refined their tools and techniques, they laid the groundwork for more complex behaviours and social cooperation, setting the stage for subsequent evolutionary and cultural developments. These advancements exemplify the resilience and ingenuity that characterized human life during one of the Earth's most formidable climatic periods. During the Ice Age, hunting and gathering strategies became increasingly sophisticated, driven by the challenging environments and fluctuating resource availability. Early humans had to adapt their methods continually, developing a nuanced understanding of their surroundings and animal behaviours. Initially, small groups relied on basic persistence hunting, chasing animals over long distances until exhaustion, an approach suited to the open, cold landscapes where large prey roamed. As they gained experience, humans refined their techniques, utilising coordinated ambushes and crafted tools such as spears and atlatls to increase hunting efficiency. These innovations allowed for more targeted procurement of large animals like mammoths, bison, and reindeer, which provided vital sustenance and materials for shelter and clothing. Gathering strategies also evolved in complexity. Early humans learned to exploit seasonal plant resources, tracking the ripening of fruits, nuts, and tubers across varied terrains. They developed knowledge of microclimates and ecological zones, enabling them to move strategically to maximize resource collection during scarce periods. This seasonal mobility required flexible social structures and communication, fostering cooperation within groups. The development of tools for processing plant materials such as scrapers and grinding stones further enhanced their ability to extract maximum nutrition from available flora. The increasing reliance on diverse resources prompted innovations in storage techniques, such as drying and fermenting foods, which extended the usability of gathered resources during harsh winters. These adaptive strategies not only ensured survival, but also contributed to social cohesion and knowledge transfer, crucial elements in the evolution of early human cultures. The need to exploit a broad spectrum of resources also spurred technological advances, including the crafting of more specialized tools for different tasks. Hunting and gathering strategies during the Ice Age grew increasingly complex as humans navigated the unpredictable environment. The pressure to adapt in a frozen world fostered innovations that laid the groundwork for more advanced behaviors. As these survival techniques evolved, they inevitably influenced the development of symbolic and artistic expressions, revealing a deeper cognitive engagement with their environment. This progression towards symbolic behavior hints at the profound relationship between environmental challenges and the emergence of human culture. The stark, dramatic landscapes of the Ice Age provided a unique canvas that profoundly influenced the emergence of early art and symbolic behavior among human populations. As glaciers sculpted the terrain, humans responded not only through survival strategies, but also by expressing their relationship with the environment. Cave paintings, carvings, and personal adornments serve as some of the earliest evidence of symbolic thought, revealing a capacity for abstract representation that transcended immediate practical needs. The confined and often illuminated spaces within caves became sanctuaries for creative expression. In these dark chambers, early humans painted images of animals, bison, horses, and reindeer, using natural pigments derived from ochre and charcoal. These depictions likely held symbolic or ritual significance, perhaps related to hunting magic or spiritual beliefs intended to influence successful hunts or honour the creatures depicted. The consistency of animal themes across different regions suggests a shared cultural importance and a developing sense of community identity rooted in their environment. Beyond cave art, personal ornaments like shell beads and animal teeth indicate an understanding of symbolism and status. Such adornments may have signalled social bonds, individual identity, or participation in group rituals. The scarcity of durable materials in the harsh climate may have heightened the significance of what could be preserved, turning simple objects into powerful symbols. The development of symbolic behavior also extended to body modification and ritual practices. Evidence of intentional burial with grave goods hints at beliefs surrounding death and an awareness of an existence beyond the physical world. This spiritual dimension, expressed through symbolic acts, underscores how early humans used art not merely for communication, but as a means of understanding and engaging with their environment and their place within it. These behaviors suggest that the Ice Age environment did more than shape survival tactics. It fostered a cognitive landscape where symbols, stories, and spiritual ideas became integral to human life. As humans grappled with the unpredictable climate, their creative expressions provided a way to interpret, influence, and find meaning amid a constantly changing world. The ebb and flow of climate during the Ice Age profoundly shaped human population dynamics, acting as both a barrier and a catalyst for migration, adaptation, and survival. Fluctuations in temperature and environmental conditions caused shifts in the availability of resources, compelling early humans to respond with remarkable resilience and ingenuity. During colder periods, expanding ice sheets and lowered temperatures reduced habitable land, constricting populations into refugia, areas where conditions remained tolerable. These refugia often became focal points for population concentration, encouraging genetic exchange and fostering cultural innovations necessary for enduring harsher climates. Conversely, warmer interglacial phases opened new territories, enabling humans to expand into previously inhospitable regions. Melting ice revealed fresh landscapes and access to new sources of food, such as migrating animals and diverse plant life. These periods of relative warmth promoted population growth and migration, dispersing groups across Eurasia and beyond. However, such expansions were rarely smooth. Sudden climate shifts could lead to abrupt habitat loss, forcing populations to retreat or adapt rapidly. This cycle of contraction and expansion created a dynamic demographic landscape, characterized by intermittent population bottlenecks and bursts of expansion, which influenced genetic diversity and evolutionary trajectories. The variability in climate also impacted technological development and social organization. In times of resource scarcity, groups innovated tools for hunting and foraging, while environmental challenges fostered complex social structures aimed at cooperative survival. For example, evidence suggests that during colder periods, humans developed more sophisticated clothing, shelter, and hunting strategies to cope with the extreme conditions. These adaptations not only ensured survival, but also laid the groundwork for cultural and technological advances that would be passed down through generations. Understanding how climate fluctuations influenced human population patterns during the Ice Age reveals the depth of human resilience and adaptability. It underscores the importance of environmental factors in shaping our evolutionary history, and offers insight into how our ancestors navigated a tumultuous, changing world. As we delve into these dynamics, it becomes clear that climate was not merely a backdrop but a driving force in the story of human evolution, an idea that naturally leads to the importance of archaeological discoveries in illuminating this complex history. The discovery of Cro-Magnon and Neanderthal remains has profoundly shaped our understanding of human adaptation and survival during the Ice Age. These ancient bones serve as tangible links to our evolutionary past, offering invaluable insights into how early humans navigated a world dominated by extreme cold, shifting landscapes, and scarce resources. The Neanderthal skeletons, for instance, reveal physical adaptations tailored for harsh environments: robust bodies, stocky builds, and enlarged nasal cavities that likely helped warm cold air before it reached the lungs. Such features exemplify how human physiology responded to the rigors of glacial climates. Cro-Magnon remains, representing early Homo sapiens, highlight the evolutionary leap toward more sophisticated tool use, cultural expression, and social organization. Their well-preserved fossils show evidence of complex behavior, from creating intricate tools and ornaments to engaging in symbolic rituals. These adaptations not only improved their chances of survival amidst the challenges of the Ice Age, but also mark the beginning of cultural evolution that would eventually lead to modern humans. The juxtaposition of Neanderthal and Cro-Magnon remains illuminates a story of both competition and interbreeding, indicating a dynamic interaction with profound implications for our genetic heritage. These discoveries go beyond mere skeletal analysis. They paint a detailed picture of human resilience and ingenuity in a brutal climate. Archaeological findings associated with these remains, such as hearths, cave paintings, and tools, further illuminate how early humans exploited their environment, hunted megafauna, and developed social bonds crucial for enduring the cold. Such evidence underscores the importance of adaptability, not just biologically but culturally, during a period of relentless environmental change. Understanding these ancient remains provides context for the broader narrative of human evolution within the Ice Age. It underscores that our ancestors were not passive victims of their environment, but active agents shaping their destiny. As we delve deeper into how early humans survived and thrived in this frozen world, it becomes clear that their story is intertwined with the Earth's climatic upheavals. This foundation sets the stage for exploring how glaciers and ice sheets physically transform the planet's surface, reshaping landscapes and influencing the course of human history. As colossal sheets of ice advanced and retreated across the landscape, their immense power fundamentally transformed Earth's surface in ways that are still visible today. Glaciers and ice sheets, acting like slow-moving geological sculptors, carved through bedrock, reshaping valleys and plains with relentless force. Their movement was driven by gravity, causing massive volumes of ice to flow outward from thick accumulations in polar regions or high-altitude zones. This slow, persistent movement exerted enormous pressure on the underlying terrain, leading to a range of erosional and depositional processes that left lasting marks on the landscape. One of the primary ways glaciers reshaped the Earth was through erosion. As they advanced, glaciers scoured the land beneath them, grinding away at rock surfaces with embedded debris and ice crystals acting like natural sandpaper. This process widened and deepened pre-existing valleys, transforming V-shaped river valleys into broad U-shaped troughs. The weight and movement of ice also caused the removal of soil and loose rock, exposing bedrock and creating rugged, often dramatic terrain. In addition to erosion, glaciers deposited vast quantities of debris, known as glacial till, as they melted. These deposits accumulated in various forms, creating features such as moraines, mounded ridges of unsorted material marking the furthest extent of glacial advance. As glaciers retreated, they often left behind a landscape dotted with lakes and wetlands, formed by meltwater accumulating in depressions carved by ice or blocked by terminal moraines. The immense scale of glacial activity also led to the formation of unique landforms that reveal the history of past ice sheets. Features like drumlins, streamlined hills shaped by moving ice, and eskers, long winding ridges formed by sediment carried within subglacial meltwater channels, stand as silent testimonies to the dynamic processes at play. These landforms not only tell stories of ancient ice movements, but continue to influence the geography and ecosystems of the regions they occupy today. Through these processes, glaciers and ice sheets have indelibly shaped Earth's surface, leaving behind a landscape marked by grandeur and complexity that reflects a history of relentless icy transformation. Glacial activity has sculpted some of the most dramatic and recognizable landforms on Earth, leaving behind features that vividly record the history of ice movement. Among these, U-shaped valleys and fjords stand out as distinctive signatures of past glacial erosion, each revealing unique aspects of the ice's power and progression. U-shaped valleys, also known as glacial troughs, form through the relentless erosion of river valleys by advancing glaciers. Unlike river valleys that tend to be V-shaped due to stream erosion, glaciers carve wide, deep troughs with steep, often nearly vertical sides. As the glacier advances, it widens and deepens the original V-shaped valley through processes like plucking and abrasion. The result is a broad, flat-bottom valley with a characteristic U-shape, often marked by hanging valleys where tributary glaciers once joined the main ice flow. These landforms serve as enduring evidence of extensive glacial erosion, illustrating the immense weight and movement of ice over millennia. Fjords, on the other hand, are a subset of U-shaped valleys that have been flooded by rising sea levels. They typically occur in regions where glaciers carved deep, steep-sided valleys below current sea level, such as in Norway, New Zealand, and parts of Canada. When glacial retreat allows seawater to flood these carved valleys, fjords are born, deep, narrow inlets with dramatic cliffs on either side. Their formation requires both powerful glacial erosion and subsequent sea level rise, which fills the valleys with seawater. Fjords are often characterized by their profound depth and picturesque landscapes, making them iconic features of glacially sculpted coastlines. Both U-shaped valleys and fjords exemplify the immense forces at work during the Ice Age. Their formation reflects not only the erosive capability of glaciers, but also the dynamic interactions between ice, land, and sea. These landforms are more than just scenic backdrops. They are vital clues to understanding the extent, movement, and retreat of glaciers across Earth's history. As we delve deeper, the next step is to explore how smaller glacial features, such as moraines, drumlins, and eskers, further reveal the story of ancient ice sheets and their monumental impact on the landscape. As glaciers advanced and retreated across the landscape, they sculpted a variety of distinctive landforms that serve as silent witnesses to their ancient journeys. Among these features, moraines, drumlins, and eskers stand out as key indicators of past glacial activity, each offering insights into the dynamics of ice movement and deposition. Moraines are accumulations of debris, rocks, soil, and unsorted sediments that are deposited directly by glaciers. They form at the edges of glaciers, marking their maximum extent or the points where the ice paused in its advance. Lateral moraines develop along the sides of an ice mass, capturing debris transported on the glacier's surface, while terminal moraines mark the furthest reach of the glacier's advance. These formations reveal not only the direction of glacial movement, but also periods of stability, helping reconstruct the extent and timing of glacial periods. Drumlins, on the other hand, are streamlined, elongated hills composed of glacial till that have been shaped by the passing ice. Their smooth, teardrop-like appearance indicates the direction of ice flow and the force exerted during deposition. Often found in clusters, drumlins suggest a dynamic process where ice sheets reworked underlying sediments, creating a landscape that records the flow patterns of glaciers over time. Their orientation and distribution can inform scientists about the direction and speed of ice movement during the last glacial maximum. Eskers are sinuous ridges formed by subglacial meltwater streams flowing beneath ice sheets. As the glacier melts, sediment-laden water deposits sand and gravel in tunnels beneath the ice. When the ice recedes, these sediment-filled tunnels are left as winding ridges. Eskers trace the pathways of subglacial drainage systems, offering clues about the dynamics of melting ice and the pathways taken by meltwater as it carved its way through or beneath the glacier. Each of these landforms encapsulates a story of glacial motion, deposition, and retreat. By studying moraines, drumlins, and eskers, geologists reconstruct the history of ice sheets, uncovering how they advanced, stalled, and withdrew across Earth's surface, testaments to the immense power of ice in shaping the planet's ancient landscapes. Glacial erosion played a pivotal role in reshaping the Earth's surface during the Ice Age, fundamentally altering the distribution and character of lakes and rivers across the landscape. As massive glaciers advanced and retreated, their immense weight and movement exerted a powerful sculpting force on the terrain beneath. The abrasive action of embedded debris and the grinding of ice against bedrock carved out deep valleys, fjords and basins, often transforming pre-existing landforms into new water-filled features. These processes created a variety of depressions, such as cirques, taons, and kettles, that later filled with meltwater, giving rise to numerous lakes, many of which are still prominent today. The uneven erosion caused by glaciers also dictated the course and flow patterns of rivers. As glaciers advanced, they often dammed existing river valleys, creating natural barriers that diverted water flow or caused temporary lakes to form upstream. When glaciers receded, these dams sometimes collapsed, releasing massive outburst floods that carved new channels and redistributed sediments. Such events left behind distinctive landforms, including streamlined hills and outwash plains, which guided subsequent river pathways. the redistribution of sediments by glacial meltwater further contributed to the complexity of drainage systems, depositing gravel, sand and silt in new configurations that dictated where rivers could meander or settle. In some regions, glacial erosion created expansive, gently sloping terrains with numerous small lakes scattered across the landscape, known as a kettle lake topography. These lakes often resulted from blocks of ice buried within glacial deposits melting slowly over time. The irregularity of erosion and deposition processes contributed to a patchwork of water bodies and waterways, influencing local ecosystems and human settlement patterns. Overall, the voracious erosive power of glaciers during the Ice Age was instrumental in carving out the modern mosaic of lakes and rivers. Their movement not only reshaped the contours of the land, but also redefined drainage networks, creating a landscape marked by intricate waterways and water-filled basins that continue to shape Earth's surface long after the glaciers receded. Understanding these processes offers crucial insights into how ancient ice sheets sculpted our planet's hydrological features. Scientists employ a meticulous process of analysing geological and sedimentary evidence to reconstruct the landscapes of past ice ages, piecing together Earth's ancient environments with remarkable detail. Central to this endeavour is the examination of landforms shaped by glacial activity, such as moraines, drumlins and outwash plains. These features serve as tangible records of ice movement, enabling researchers to infer the extent and dynamics of past glaciers. By mapping these landforms across regions, scientists can reconstruct the configuration of ice sheets and their retreat patterns over millennia. Sedimentary deposits also offer crucial insights. For instance, layers of glacial till, unsorted sediments deposited directly by ice, preserve snapshots of ice, advance and retreat. Detailed stratigraphic analysis of these layers reveals changes in climate conditions, sediment sources, and ice coverage over time. Similarly, the presence of varves, seasonally layered sediments in lakes, provides annual resolution of environmental conditions, capturing fluctuations in temperature, precipitation, and ice melt cycles during the Ice Age. Furthermore, scientists analyze chemical signatures within sediments to identify past environmental conditions. Isotopic analyses, such as oxygen isotope ratios in marine and terrestrial sediments, help determine historical temperatures and ice volumes. These isotopic markers serve as proxies, translating sediment composition into climate data that informs models of ice sheet behaviour. Paleobotanical and microfossil records embedded within sediment layers also to landscape reconstructions. Pollen grains and microscopic organisms trapped in sediments reveal vegetation patterns and ecological zones that persisted during different phases of glaciation. This information helps reconstruct not only the physical landscape, but also the climate context that supported various ecosystems. Advances in remote sensing and geochronology have refined these methods further. Techniques like radiocarbon dating and optically stimulated luminescence enable precise dating of sediment layers, establishing a chronological framework for landscape changes. Combined, these diverse lines of evidence allow scientists to create dynamic reconstructions of Ice Age landscapes, revealing how glaciers sculpted the terrain and influenced Earth's surface over tens of thousands of years. This reconstruction process provides a foundation for understanding how these ancient landscapes continue to shape our environment today. The enduring imprint of glacial landscapes continues to influence modern geography in profound and diverse ways. As glaciers advanced and retreated over tens of thousands of years, they sculpted the Earth's surface, creating features that persist long after the ice itself has vanished. These features serve as a physical record of past climatic shifts, while also shaping the environment in ways that affect ecosystems, human activity, and land use today. One of the most notable long-term effects of glacial activity is the formation of distinct landforms such as U-shaped valleys, fjords, and moraines. U-shaped valleys, carved by enormous ice sheets grinding through mountain ranges, remain striking features that define many alpine regions. Fjords, deep, glacially carved inlets, cut into coastlines, especially in places like Norway and New Zealand, providing unique habitats and influencing local weather patterns. Moraines, accumulations of till and debris left behind by retreating glaciers, create fertile plains and serve as natural reservoirs of groundwater, shaping agriculture and settlement patterns in many regions. Glacial erosion and deposition have also significantly altered drainage systems and sediment distribution. The redistribution of sediments has led to the development of extensive alluvial plains and deltic systems that influence modern river courses and coastal ecosystems. These deposits impact soil fertility, shaping agricultural practices and influencing biodiversity. Perhaps most enduring are the changes to the Earth's crust itself. Glacial weight depressed the land beneath ice sheets, causing isostatic depression. When the glaciers receded, this depression gradually rebounded, a process known as isostatic rebound, altering local topographies and creating new landforms. In some coastal areas, this uplift has raised former seabeds above sea level, influencing current shoreline configurations and ocean current patterns. The legacy of glacial landscapes extends beyond physical features. These features influence contemporary climate regulation, as glacial valleys and lakes can affect local microclimates. In many regions, the remnants of Ice Age glaciers continue to serve as vital freshwater sources, shaping ecosystems and human economies alike. As a testament to their lasting influence, glacial legacies remain embedded in the very fabric of Earth's surface, continuously moulding the environment long after the last ice has melted. As glaciers receded from the landmass, their retreat left behind a landscape forever altered, with coastlines bearing the unmistakable scars of this monumental transformation. The melting of these colossal ice sheets did more than just expose new land. It actively sculpted the contours of modern coastlines through a combination of erosional and depositional processes. As glaciers shrank, their immense weight was gradually lifted from the Earth's crust, allowing it to undergo isostatic rebound, a slow uplift that elevated former glacier beds and adjusted coastline elevations over millennia. The retreating ice front also left behind vast quantities of meltwater, which flooded low-lying coastal areas, creating extensive inland seas and fjords. These deep, glacially carved inlets became defining features of regions such as Scandinavia, New Zealand, and parts of North America. The process of glacial erosion carved out U-shaped valleys and steep fjord walls, which upon flooding formed some of the most dramatic coastlines on Earth. These submerged glacial valleys not only shaped the physical landscape, but also influenced patterns of ocean circulation and marine ecosystems. Sediment deposition played a crucial role as well. As glaciers retreated, they deposited unsorted till, gravel and silt along coastlines, forming features such as moraines and drumlins that sometimes extended into the sea. Over time, wave action and tidal processes reworked these deposits, creating barrier islands, deltas and estuarine environments that are characteristic of post-glacial coastlines today. Such features often serve as rich habitats for diverse flora and fauna, illustrating how Ice Age processes continue to influence ecological patterns. The combination of glacial erosion, isostatic adjustments, and sediment deposition resulted in coastlines with complex geometries, fjords, estuaries, and barrier islands that define many of Earth's most iconic shores. These landscapes stand as enduring testimonies to the immense power of ice and the dynamic forces that continue to shape Earth's surface long after the glaciers have vanished. Understanding how the Ice Age glaciers shaped coastlines provides insight into ongoing geological processes and the evolving character of our planet's edges. Permafrost and periglacial processes have profoundly influenced the landscapes of Earth's cold regions, leaving a legacy that continues to shape these environments long after the peak of glaciation. Permafrost, permanently frozen ground, acts as a fundamental substrate in polar and subpolar zones, affecting both surface and subsurface features. Its presence stabilizes soil and rock, preventing widespread erosion but also creating unique landforms such as patterned ground, pingos, and thermokarst terrain. These features emerge from cycles of freezing and thawing, which fragment and reshape the landscape over millennia. Periglacial processes, closely linked to the presence of permafrost, drive the formation of a variety of distinctive landforms. For instance, frost heaving, the upward movement of soil and rock caused by the expansion of freezing water, leads to the development of patterned grounds, including sorted circles and stripes. These patterns reflect the ongoing struggle between ice-rich soils and seasonal temperature fluctuations. In regions where permafrost is susceptible to thawing, thermokarst landscapes develop, characterized by irregular depressions, sinkholes, and uneven terrain resulting from ground subsidence. Such features not only alter the physical landscape, but also influence hydrology, creating lakes, ponds, and wetlands that are vital habitats. The stability and distribution of permafrost are intricately linked to climatic conditions, with colder periods during the Ice Age promoting extensive permafrost coverage. As temperatures fluctuated, periglacial processes intensified, carving out complex surface patterns and influencing sediment transport. These processes also contributed to the redistribution of sediments and organic material, impacting local ecosystems and carbon cycles. When the climate warmed at the end of the last Ice Age, permafrost began to thaw, releasing stored greenhouse gases and transforming the landscape dramatically. The role of permafrost and periglacial processes reveals a landscape in constant flux, shaped by the shifting climate and the dynamic interactions of ice, soil, and water. Their legacy provides crucial insights into how Earth's surface responds to freezing and thawing cycles, setting the stage for understanding the climatic changes that marked the end of the last Ice Age and the transition to a warmer world. The end of the last Ice Age was heralded by a series of profound and complex climatic shifts that transformed Earth's surface and atmospheric conditions. As the planet gradually warmed, these changes were driven by a combination of factors that disrupted the delicate balance maintaining the icy grip of glacial periods. Central to this transition was a significant increase in global temperatures, which initiated the melting of vast ice sheets that had spread across North America, Eurasia, and other regions. This warming was not uniform but resulted from a combination of declining ice albedo feedback, shifts in atmospheric greenhouse gases, and alterations in oceanic and atmospheric circulation patterns. A key climatic change involved the redistribution of heat across the planet. As ice sheets diminished, dark land and water surfaces replaced reflective ice, absorbing more solar energy and reinforcing the warming trend. Simultaneously, fluctuations in greenhouse gases such as carbon dioxide and methane, initially released from melting permafrost and oceanic sources, further amplified the warming. These gases trap heat in the atmosphere, strengthening the greenhouse effect and accelerating ice melt. Volcanic activity, though episodic, also contributed to atmospheric composition changes, sometimes temporarily cooling, but generally playing a minor role relative to greenhouse gases. Changes in ocean currents and atmospheric circulation patterns contributed significantly to the end of ice conditions. The melting ice altered salinity levels and ocean stratification, which in turn affected the strength and direction of major currents responsible for redistributing heat around the globe. These shifts helped maintain the warmer climate by transporting heat toward the poles and equator more effectively than during glacial periods. The retreat of ice sheets also led to dramatic reductions in surface albedo, exposing darker land and ocean surfaces that absorbed more sunlight. This positive feedback loop further accelerated the warming process. As the ice retreated, the landscape transformed, opening new migration routes and habitats, but also setting the stage for the subsequent rise in sea levels. Understanding these climatic changes offers insight into the profound transition from the frozen world of the last Ice Age to the relatively warm and stable climate we experience today. This transition not only reshaped Earth's surface, but also set the stage for the dynamic interactions between climate, sea levels, and coastlines that continue to influence our planet. As the vast ice sheets that once blanketed much of the northern hemisphere began their slow retreat, their influence extended far beyond the mere reshaping of the landscape. The melting of these colossal ice masses caused a significant rise in global sea levels, a phenomenon that profoundly altered coastlines and reshaped entire continents. During glacial periods, immense volumes of water were stored in ice sheets, causing sea levels to drop as oceans contracted. When warming initiated their retreat, this stored water was released back into the oceans, leading to a series of rapid and often dramatic rises in sea levels. This rise in sea levels had immediate and far-reaching impacts on coastal regions worldwide. Low-lying areas, once submerged or fringed by ice, were suddenly transformed into expansive shallow seas or fertile coastal plains. Some landforms, such as vast continental shelves, became exposed during glacial maxima, only to be flooded again during interglacial stages. These fluctuations created a dynamic and constantly changing shoreline landscape, influencing sediment deposition, erosion patterns, and the distribution of ecosystems. The inundation of coastal zones also affected human and animal populations. As coastlines shifted, habitats were submerged or exposed, forcing species to adapt, migrate, or face extinction. For early humans, these changes could mean access to new resources or the loss of familiar hunting grounds. For marine life, the changing depths and salinity gradients influenced the distribution of nutrients and the development of diverse marine communities. The retreat of ice sheets also contributed to the redistribution of fresh water and the alteration of ocean currents. As massive ice masses melted, freshwater influxes into the oceans could temporarily disrupt established circulation patterns, impacting global climate systems. These shifts not only affected regional weather patterns, but also played a role in stabilizing or destabilizing subsequent climate cycles. In sum, the melting of ice sheets during deglaciation phases was a catalyst for transforming the planet's coastlines and sea levels, setting the stage for ongoing ecological and geological evolution that continues to shape the Earth's surface long after the ice has receded. As the climate shifted from glacial to interglacial periods, the environment underwent profound transformations that shaped the Earth's ecological landscape. This transition, driven by subtle variations in Earth's orbit and atmospheric composition, triggered a cascade of environmental and ecological impacts. As glaciers receded, vast new habitats emerged, transforming the physical geography and opening opportunities for diverse ecosystems to flourish. One of the most significant changes involved the redistribution of water resources. Melting ice contributed to rising sea levels, inundating low-lying coastal regions and altering oceanic circulation patterns. These shifts influenced temperature and salinity gradients, which in turn affected marine life distribution and productivity. The redistribution of fresh water also impacted river systems, creating new pathways and changing sediment transport, which fostered the development of fertile floodplains and wetlands. Such areas became hotspots for plant growth, supporting a surge in terrestrial biodiversity. The retreat of ice sheets exposed previously glaciated terrains, allowing pioneer species such as hardy grasses and shrubs to establish themselves on newly available land. These early colonizers laid the foundation for more complex ecosystems, attracting herbivores and predators alike. The increased availability of plant life provided vital energy sources, fueling the expansion of herbivorous mammals and facilitating shifts in food webs. As temperature and precipitation patterns stabilized, forests began to re-establish in many regions, creating dense habitats that supported a multitude of species. Ecologically, this period marked a pivotal shift toward greater biodiversity. Species adapted to the colder conditions either migrated northward or retreated to refugia, while others evolved new traits suited for warmer environments. The changing climate also prompted evolutionary pressures that led to speciation and extinction events, reshaping community compositions. These dynamic processes fostered a new equilibrium, setting the stage for the complex ecosystems observed in modern interglacial periods. Understanding these environmental and ecological impacts highlights the interconnectedness of climate and life. The transition from ice to warmth did not merely reshape landscapes, but also redefined the relationships among species, ecosystems, and the planet itself. This intricate dance of change laid the groundwork for the biological diversity we see today, and prompts us to consider how current climate shifts may similarly influence Earth's future. As the icy grip of the last ice age receded, the planet's flora and fauna faced a landscape transformed by rapid and dramatic climate shifts. Species that had thrived in harsh, cold environments had to adapt quickly or face extinction. Many plant species responded through migration, seeking refuge in areas with more favourable conditions. For instance, tundra vegetation shifted northward, following the retreating ice sheets, establishing new habitats in previously uninhabitable regions. These moving plant communities often formed the foundation for emerging ecosystems, supporting herbivores and, subsequently, predators. Animals exhibited a variety of responses to the warming climate. Large megafauna such as mammoths, woolly rhinoceroses, and saber-toothed cats were pushed into isolated refugia as their expansive habitats shrank. Some managed to survive in pockets of cold, high altitude or northern regions, but many faced extinction due to the rapid pace of change and human pressures. Smaller, more adaptable species, like deer, elk, and various rodents, expanded their ranges, capitalizing on the newly available vegetation and open landscapes. Bird species, many of which are highly migratory, adjusted their migration timings and routes to align with shifting plant phenology, ensuring access to food sources during breeding and migration seasons. The end of the Ice Age also introduced a cascade of ecological shifts. As glaciers melted, fresh water flooded into oceans, altering salinity and current patterns that influenced marine life distribution. Fish populations responded by migrating to new breeding grounds, while marine mammals expanded into newly accessible coastal areas. Forests replaced tundra in many regions, creating complex habitats that supported a broader diversity of wildlife. These environmental transformations fostered evolutionary pressures, leading to speciation and adaptation among many species. The dynamic responses of plants and animals during this transitional period exemplify nature's resilience and versatility. Yet, the pace of change placed significant stress on many species, prompting extinctions and migrations that forever shaped the biological tapestry of post-Ice Age Earth. The intricate interplay between climate shifts and biological responses underscores the profound influence of environmental change on life's evolution. As the Ice Age drew to a close, human activity emerged as a significant force shaping the evolving landscapes and ecosystems of the glacial world. Early humans, equipped with primitive tools and adaptive strategies, began to influence their environment in ways that would leave lasting impressions. While their impact was initially subtle, primarily through hunting, gathering, and migration, these activities gradually transformed the landscape, setting the stage for the development of agriculture and settled communities. One notable way humans affected post-Ice Age environments was through megafaunal extinction. As human populations expanded into new territories, their hunting practices contributed to the decline and eventual disappearance of many large mammals, such as mammoths and saber-toothed cats. These extinctions altered ecological balances, affecting vegetation patterns and nutrient cycles. The loss of these keystone species often led to significant shifts in plant communities, influencing the structure and composition of the emerging forests and grasslands. Agriculture represented a pivotal turning point. As humans transitioned from nomadic foraging to settled farming, they began actively modifying their surroundings, clearing land for crops, constructing irrigation systems, and domestication of plants and animals intensified landscape transformation. These activities accelerated soil erosion, altered local hydrology, and introduced new species into ecosystems, often outcompeting native flora and fauna. Urbanization and deforestation in later periods further reshaped environments. As populations grew, forests were cleared to accommodate expanding settlements and natural habitats were fragmented. This human footprint contributed to climate feedback mechanisms, such as increased greenhouse gas emissions from land use changes, which could influence climate patterns and the pace of environmental change. Overall, human activity played an increasingly influential role in the post-Ice Age environment, transitioning from a relatively passive participant to an active agent of ecological transformation. These early interactions laid the groundwork for the complex human-environment relationships that continue to shape our planet today. Recognizing this influence helps us appreciate the deep-rooted connection between human development and environmental change, a relationship that remains central to understanding both past and future climate dynamics. To unravel the timing and progression of Ice Age terminations, scientists employ a suite of sophisticated dating techniques rooted in geochronology and paleoclimatology. Central to these efforts are methods like radiocarbon dating, which measures the decay of carbon-14 in organic materials up to about 50,000 years old. When studying ice cores, sediments, or fossilized remains, radiocarbon provides precise age estimates for relatively recent transitions, such as the end of the last glacial period. For older events, especially those extending beyond the radiocarbon limit, scientists turn to isotope ratio analyses, notably oxygen isotopes, 16O and 18O. The ratio of these isotopes in ice cores or marine sediments serves as a powerful proxy for past temperatures and ice volume. Fluctuations in oxygen isotope ratios reveal detailed timing of ice sheet growth and melting, allowing researchers to pinpoint when glaciers retreated or advanced with remarkable resolution. Another vital tool involves the examination of layered sediment deposits and ice cores, which preserve annual or even seasonal information. Variations in dust, volcanic ash layers, or trapped gas bubbles within these cores offer chronological markers. Volcanic ash layers, or tephra for instance, serve as chronological tie points across different sites, linking ice core records to global events. Furthermore, scientists utilize astronomical tuning, also known as orbital tuning, which aligns isotope records with calculated variations in Earth's orbital parameters, eccentricity, obliquity, and precession. By matching periodicities and climate proxies to known orbital cycles, researchers can refine the timing of deglaciation events with high precision, constructing a detailed timeline of how ice sheets responded to changes in Earth's orbit. These methods, when integrated, create a comprehensive framework for understanding the complex dynamics of ice age terminations. They reveal not just the approximate dates of glacial retreat, but also the nuanced pace and sequence of environmental shifts, offering insights into whether these transitions unfolded gradually or abruptly in response to evolving climate forcings. The question of whether ice age terminations unfolded suddenly or over gradual periods has long intrigued scientists, sparking diverse hypotheses grounded in paleoclimatic evidence. Recent research suggests that the transition from glacial to interglacial conditions often involved a complex interplay of rapid shifts and slow evolutions, challenging earlier notions of a purely gradual process. One prominent theory posits that certain abrupt climate events, such as the Buling-Allerud warming around 14,700 years ago, occurred on timescales of decades to centuries, indicating that some parts of the Ice Age end could happen swiftly. These rapid events are often associated with sudden releases of stored greenhouse gases, particularly methane, from thawing permafrost and subglacial lakes, which amplify warming and accelerate ice melt. Such feedback mechanisms could induce tipping points, where the climate system shifts rapidly from a glacial to an interglacial state. Conversely, other evidence supports a more gradual transition, driven by the slow but persistent changes in Earth's orbital parameters, oceanic circulation, and greenhouse gas concentrations. These factors gradually alter insolation patterns and sea levels, steadily diminishing ice sheet extents over millennia. The interplay between these gradual forcings and episodic abrupt events creates a mosaic of transition dynamics, with some periods marked by swift climatic swings and others characterized by prolonged steady change. Advancements in ice core and sediment analyses have revealed that the end of previous ice ages was not a uniform process, but rather a series of oscillations, interspersed with rapid warming episodes, culminating in a relatively stable interglacial period. This nuanced understanding underscores that climate system responses are multifaceted, involving both tipping points and incremental shifts. Recognizing these patterns not only illuminates past climate behavior, but also informs models predicting how current and future climate systems might respond to ongoing human influences. By examining the processes that mark the end of past ice ages, scientists gain critical insights into the mechanisms that drive large-scale climate shifts. These historic transitions reveal how Earth's climate system responds to complex interactions among atmospheric composition, oceanic processes, and terrestrial feedbacks. For example, the abrupt warming events known as Dansgaard-Oeschger cycles, which punctuated the deglaciation periods, highlight the potential for rapid climate change driven by feedback loops within the climate system. Understanding these episodes demonstrates how small initial perturbations, such as shifts in greenhouse gases or ocean circulation, can trigger swift and profound temperature increases. Reconstructing the timing and pace of past deglaciations has also shed light on the role of ice sheet dynamics and climate regulation. As ice sheets melted, their retreat influenced global sea levels, altered Earth's albedo, and disrupted ocean currents that helped distribute heat around the globe. These feedback mechanisms often amplified warming, leading to further melting and climate instability. Recognizing the thresholds and tipping points that led to these transitions enables scientists to identify similar vulnerabilities in the current climate system. Moreover, Paleoclimate records reveal the importance of ocean-atmosphere interactions, particularly the role of ocean circulation patterns such as the Atlantic Meridional Overturning Circulation, AMOC, in regulating climate during deglaciation. Changes in freshwater input from melting ice affected salinity and density-driven currents, causing shifts in heat distribution that accelerated warming phases. Such insights emphasize the interconnectedness of Earth's components and demonstrate how disruptions in one part of the system can cascade into widespread climate change. By studying the end of past ice ages, researchers develop models that better simulate potential future scenarios. These models incorporate the feedbacks, thresholds, and response times observed historically, helping policymakers understand the risks of rapid climate shifts today. Ultimately, the lessons from Earth's climatic past serve as a vital compass, guiding predictions and responses as we confront the ongoing challenges of climate change. During the immense climatic shifts of the Ice Age, the world's oceans did not remain static, but instead experienced profound changes in their salinity, temperature, and circulation patterns. As glaciers expanded and vast ice sheets locked water onto land, ocean levels fell, exposing continental shelves and disrupting established currents. These alterations had a cascading effect on oceanic properties, reshaping the marine environment in ways that echoed across global systems. The accumulation of ice effectively removed significant amounts of freshwater from the oceans, leading to increased salinity in certain regions where evaporation exceeded precipitation, while other areas experienced dilution. This uneven distribution of salinity influenced the density of seawater, which in turn affected thermohaline circulation, the global conveyor belt responsible for redistributing heat and nutrients across the planet. For example, in the North Atlantic, increased freshwater input from melting ice during deglaciation episodes temporarily weakened these currents, causing shifts in climate patterns both locally and globally. Temperature variations in the ocean were closely tied to ice sheet dynamics, with colder surface waters forming over expanded ice-covered regions. These colder waters often contributed to the strengthening of sea ice, further insulating the ocean and reducing heat exchange with the atmosphere. Conversely, during warmer interstadial periods, the melting of ice sheets released vast quantities of fresh water into the ocean, disrupting established temperature gradients and circulation pathways. The restructuring of circulation patterns during glaciations had far-reaching impacts on nutrient distribution, marine ecosystems, and climate regulation. Changes in currents could isolate or connect different ocean basins, affecting the exchange of heat and salinity on a planetary scale. These shifts in ocean dynamics played a crucial role in amplifying or mitigating ice sheet growth, creating feedback loops that sustained or reversed glacial advances. Understanding these complex interactions underscores the importance of oceanic responses during the Ice Age. Their influence extended beyond mere climate modulation, fundamentally altering the chemistry and flow of the world's oceans, an enduring legacy visible today in the submerged landscapes and geological records that hold clues to these dramatic shifts. Submerged landscapes provide a remarkable window into the dynamic sea level fluctuations characteristic of Ice Age periods. During these colder intervals, vast volumes of water were locked within expansive ice sheets, causing global sea levels to drop significantly, sometimes by as much as 120 meters below present-day levels. This dramatic lowering of sea levels exposed continental shelves that are now submerged, creating land bridges and broad coastal plains accessible to early humans and migrating species. The physical evidence of these changes manifests clearly in submerged topography, revealed through marine geology and high-resolution sonar mapping. Underwater terraces, for instance, mark former coastlines, while submerged river valleys, known as paleo valleys, trace routes once carved by flowing fresh water before being inundated by rising seas. The North Sea, for example, contains extensive submerged landscapes that once served as terrestrial corridors, illustrating how lowered sea levels created land corridors, facilitating migration across Europe and Asia. Similarly, submerged terraces along the Atlantic coasts of North America and Europe point to previous shoreline positions, confirming the extent of sea level fluctuations. Coral reefs and drowned shoreline features also serve as crucial indicators, During periods of low sea levels, many reefs grew atop now exposed landforms, their fossilized remains preserved beneath the ocean surface, providing a snapshot of sea levels at specific intervals. Sediment cores extracted from these submerged regions further reveal changes in water depth and climate, offering chronological records of sea level variation. These data, combined with radiocarbon dating of organic material found within submerged deposits, help reconstruct a timeline of sea level change with remarkable precision. This submerged landscape evidence is not only vital for understanding past sea level dynamics, but also underscores the profound impact of Ice Age climate shifts on the Earth's surface. As ice sheets advanced and retreated, they continuously reshaped coastlines and land-sea boundaries, leaving behind a submerged legacy of a world in constant flux. Such insights deepen our appreciation of how climate oscillations have historically sculpted the planet's geography, setting the stage for human migrations and ecological transformations. The emergence of land bridges such as Beringia profoundly shaped the patterns of migration and species dispersal during the Ice Age. As massive ice sheets advanced and retreated, sea levels fluctuated dramatically, sometimes dropping as much as 120 meters below current levels, exposing vast stretches of continental shelf. These newly uncovered land corridors created pathways that had been submerged during interglacial periods, effectively transforming the geography of the Northern Hemisphere. Beringia, connecting Asia and North America, exemplifies how such land bridges served as vital routes for both humans and animals. During periods of lowered sea levels, terrestrial mammals like mammoths, bison, and camels migrated across these corridors, exploiting the abundant resources of the expanding tundra. Human groups, likely following migrating game, also utilize Beringia, facilitating one of the earliest known peopling of the Americas. These migrations were not mere movements of individual species, but contributed to complex ecological exchanges, leading to genetic mixing and the spread of flora and fauna across continents. The accessibility of these land bridges also prompted significant evolutionary events. Isolated populations, separated by the ice sheets and vast oceans during interglacial intervals, diverged and evolved independently, fostering regional diversity. Conversely, during glacial maxima, species adapted to cold environments rapidly expanded into new territories, sometimes resulting in the emergence of specialized subspecies or even new species owing to the fragmented and shifting habitats. In addition to shaping migration routes, land bridges influenced ecological dynamics and intercontinental interactions. They facilitated not only species dispersal, but also the spread of pathogens and symbiotic relationships, weaving a complex web of biological exchanges. When the ice sheets receded and sea levels rose again, these pathways were submerged, constraining species to their new, often isolated habitats, and setting the stage for subsequent evolutionary trajectories. As we consider how these land bridges dictated migration patterns, it becomes clear that their formation was a pivotal factor in the biological and cultural transformations of the Ice Age world. This naturally leads to pondering how shifting ocean currents further altered the global climate during these dynamic periods. Shifts in ocean currents during the Ice Age profoundly influenced global climate by redistributing heat across the planet's surface. As ice sheets expanded and contracted, they altered the distribution of land masses and the configuration of the ocean basins, which in turn modified the pathways and strength of major currents, such as the Gulf Stream and the Antarctic Circumpolar Current. These changes had a cascading effect on climate patterns, especially in regions distant from the ice sheets themselves. During glacial periods, the buildup of massive ice sheets in the northern hemisphere disrupted the typical flow of warm equatorial waters toward higher latitudes. This often resulted in a weakening or rerouting of the Gulf Stream, diminishing the transfer of heat from the tropics to northern Europe and North America. The reduced heat delivery contributed to the colder, more stable conditions characteristic of an ice age. Conversely, in some areas, the rerouting of currents intensified cold surface waters, promoting sea ice expansion and further cooling regional climates. The redistribution of oceanic heat also influenced the strength and position of the thermohaline circulation, the global conveyor belt driven by differences in water density. During colder periods, Increased formation of sea ice and the influx of fresh water from melting glaciers could disrupt this circulation, creating a bottleneck that slowed heat transfer across the oceans. This slowdown reinforced the cooling trend, establishing a feedback loop that maintained the frigid conditions. Conversely, when climate warmed and glaciers receded, the influx of fresh water diminished, allowing the thermohaline circulation to resume its vigorous state, redistributing heat more evenly and tempering global cooling. These modifications in ocean currents not only affected temperature regulation, but also played a key role in controlling the distribution and intensity of storms, monsoons, and precipitation patterns. Such shifts could trigger widespread ecological and atmospheric changes, influencing the stability of ice sheets and the global climate system as a whole. As scientists continue to unravel the complex interplay between ocean currents and climate during the Ice Age, it becomes clear that these vast dynamic flows were central to shaping the planet's climatic history. This understanding naturally leads to questions about how freshwater inputs, particularly from icebergs, later impacted oceanic circulation and climate stability. Icebergs and freshwater input exerted profound influences on oceanic circulation and climate systems during the Ice Age, shaping the broader environment in complex ways. Massive icebergs carved from expanding ice sheets often drifted into ocean basins, releasing volumes of fresh water into marine systems. These episodic influxes of fresh water had the potential to disrupt established ocean currents, particularly the thermohaline circulation, which is driven by differences in water density influenced by temperature and salinity. When large quantities of fresh water entered the North Atlantic and other key oceanic gateways, they diluted seawater salinity, reducing its density and impeding the sinking of dense, cold water that normally fuels deep-water currents. This disruption could weaken the Atlantic meridional overturning circulation, AMOC, leading to dramatic regional cooling due to reduced heat transport from equatorial regions. Such freshwater pulses often coincided with abrupt climate shifts, known as Dansgaard-Oeschger events, which manifested as rapid warming followed by cooling episodes within the broader glacial periods. In addition to immediate thermal effects, the influx of freshwater influenced sea ice extent and stability. Increased freshwater input could promote the expansion of sea ice, which further insulated the ocean from atmospheric heat exchange, amplifying cooling tendencies. Conversely, periods of reduced freshwater input often aligned with warmer interstadial phases, allowing for the re-establishment of vigorous ocean currents and the redistribution of heat globally. The role of freshwater and icebergs extended beyond regional impacts. They contributed to the cyclical nature of climate variability during the Ice Age. Variations in iceberg carving and meltwater input were intimately linked with the growth and decay of ice sheets, creating feedback loops that modulated not only local environments but also global climate patterns. Understanding these dynamics requires examining how episodic freshwater forcing influenced the delicate balance of oceanic and atmospheric systems, setting the stage for how scientists now interpret ancient climate records through sediment and isotopic analyses. To unravel the mysteries of past oceanic conditions during the Ice Age, scientists turned to an array of innovative techniques centered around sediment cores and isotopic analysis. These methods serve as ancient archives, preserving a wealth of information that allows researchers to reconstruct climate variability and ocean dynamics with remarkable precision. Sediment cores, extracted from the ocean floor, act as time capsules, containing layers of sediments that accumulated over millennia. As particles settle from the water column, they carry with them signs of the environment at the time of deposition, such as mineral content, organic material, and microfossils. By examining the composition and layering of these sediments, scientists can infer changes in ocean productivity, circulation patterns, and even the extent of ice cover. For instance, variations in the types and abundance of microfossils can reveal shifts in nutrient availability and water temperature, painting a detailed picture of past ocean conditions. Complementing sediment analysis, isotopic analysis probes the chemical signatures embedded within these sediments. Stable isotopes of oxygen, particularly oxygen-18, (18O), and oxygen-16, (16O), are especially informative. The ratio of these isotopes in calcium carbonate shells of marine microfossils reflects the temperature and volume of global ice sheets at the time they formed. During colder periods, more 16O is locked in ice sheets, enriching ocean waters with 18O. When these shells are analysed, they reveal fluctuations in global ice volume and temperature. Similarly, isotopic signatures of carbon and other elements provide insights into ocean productivity and carbon cycling, which are closely linked to climate shifts. Combining sediment stratigraphy with isotopic data enables scientists to reconstruct detailed timelines of ocean temperature changes, sea level fluctuations, and circulation variations across different ice age intervals. These reconstructions not only deepen understanding of past climate systems, but also serve as vital analogues for contemporary oceanic and atmospheric changes, offering clues about the Earth's response to ongoing climate variability. As research advances, integrating these techniques continues to refine our grasp of the complex interactions that have shaped our planet's climate history. The profound shifts in oceanic conditions during the Ice Age offer critical insights into the mechanisms driving climate variability today. During glacial periods, significant reductions in sea levels, often dropping by over 100 meters, reshaped coastlines and altered the distribution of nutrients and heat within marine systems. These changes disrupted established ocean circulation patterns, particularly the thermohaline conveyor belt, which plays a vital role in regulating global climate by redistributing warm and cold water masses. Evidence from sediment cores reveals that the intensification and weakening of these currents correlated closely with climate fluctuations, highlighting their sensitivity to shifts in ice sheet extent and freshwater input from melting or accumulating ice. The expansion and contraction of large ice sheets also impacted the salinity and temperature gradients in the North Atlantic and Southern Oceans, influencing the strength and stability of oceanic pathways. These variations in ocean circulation contributed to periods of rapid climate change, with some regions experiencing abrupt cooling or warming based on the modulation of heat transport. Studying these past oceanic responses helps reveal the feedback mechanisms between ice sheets, ocean currents, and atmospheric conditions, emphasizing the interconnectedness of Earth's climate system. Furthermore, the melting of ice sheets during deglaciation phases released massive freshwater pulses into the oceans, often destabilizing currents and triggering climate shifts on a global scale. These episodes serve as modern analogues for understanding potential future scenarios where freshwater influx, due to accelerated melting, might disrupt current circulation patterns, possibly leading to abrupt climate events. The implications extend beyond mere historical curiosity. They underscore the importance of oceanic stability in maintaining climate equilibrium. Recognizing how past oceanic changes contributed to climate variability enhances our ability to interpret current shifts, such as the weakening of the Atlantic meridional overturning circulation, which could have far-reaching impacts on regional and global climates. As we continue to decipher these ancient oceanic patterns, their lessons remain vital for predicting and mitigating future climate fluctuations, emphasizing the ocean's central role in Earth's climate resilience. During the tumultuous climate swings of the Ice Age, marine life faced both profound challenges and remarkable opportunities for adaptation. As glaciers expanded and contracted, sea levels fluctuated dramatically, reshaping coastlines and altering the aquatic landscape. These changes prompted marine organisms to develop a range of survival strategies. Many species migrated vast distances to remain within their preferred temperature zones, often moving from low-latitude tropical regions toward cooler northern or southern waters as ice sheets advanced. Conversely, some species expanded their ranges during periods of retreat, colonizing newly exposed continental shelves and shallow seas created by falling sea levels. Adaptations in physiology also played a crucial role. Cold-adapted species developed thicker insulating layers, blubber in marine mammals and denser shells in mollusks, allowing them to withstand lower temperatures. Certain planktonic communities, which form the foundation of marine food webs, evolved to thrive in the changing nutrient regimes associated with varying ocean currents and ice cover. The formation of seasonal polynyas, areas of open water amidst sea ice, became critical habitats for feeding and breeding, supporting diverse communities despite the encasing ice. The dynamic nature of the ice sheets influenced not only where marine species could survive, but also how they interacted within ecosystems. As ice retreated, new habitats emerged, prompting rapid colonization by benthic and pelagic species. In some cases, isolated populations adapted to unique conditions, leading to speciation events. Conversely, during extensive glaciations, the reduction of open water restricted movement and gene flow, causing population bottlenecks and local extinctions. Marine life's resilience during these fluctuating conditions underscores the intricate link between climate dynamics and biological adaptation. These patterns of migration, physiological change, and ecological shifts left detectable traces in the fossil record, offering vital clues about past environmental conditions. Understanding how marine organisms responded to Ice Age variability not only illuminates the history of life on Earth, but also enhances our ability to predict how current climate changes might influence marine ecosystems. As we delve into the methods scientists employ to uncover these ancient stories, it becomes clear that deciphering the past is integral to understanding the future of our planet's frozen and aquatic worlds. Piecing the story of Earth's icy past relies on a suite of sophisticated dating techniques that allow scientists to assign accurate ages to sediments and fossils from Ice Age epochs. Central to this endeavour are methods that analyse physical, chemical, and isotopic properties of samples, each offering unique insights into the timing of glacial events and the life they supported. One of the foundational techniques is radiometric dating, which measures the decay of naturally occurring isotopes within minerals. For example, uranium series dating can be applied to calcium carbonate formations, such as stalagmites within caves, providing age estimates spanning hundreds of thousands of years. Similarly, potassium-argon (Kr) and argon-argon (Rr) dating are instrumental in dating volcanic ash layers embedded within sediments. The presence of these tephra layers acts as precise chronological markers, helping to bracket the ages of associated sediments and fossils. Complementing radiometric methods are biostratigraphy and paleomagnetic dating. Biostratigraphy involves identifying and correlating fossil assemblages, such as pollen, microfossils, or animal remains, whose evolutionary timelines are well established. By comparing fossil types across different sites, scientists can infer relative ages and reconstruct migration patterns. Paleomagnetic dating examines the Earth's historical magnetic field reversals recorded in rocks and sediments. Since geomagnetic reversals are globally synchronized events, their identification within sediment layers provides a robust chronological framework. Another vital approach is luminescence dating, including optically stimulated luminescence (OSL) and thermoluminescence (TL). These techniques measure the accumulation of trapped electrons in mineral grains exposed to sunlight or heat, respectively. When sediments are buried, the trapped energy begins to accumulate at a known rate, allowing scientists to calculate the time elapsed since the sediments were last exposed to sunlight or heat. Together, these methods create a detailed temporal map of Ice Age sediments and fossils. By integrating multiple approaches, researchers can reconstruct a nuanced timeline of glacial advances, retreats, and associated biological shifts. This multidimensional dating framework provides the backbone for understanding the complex dynamics of Earth's Ice Age history, offering clues that extend even to the atmospheric and climatic conditions of past eras, a natural segue into how ice cores reveal the stories locked within ancient polar archives. Ice cores serve as remarkable archives of Earth's climatic history, offering an unparalleled window into past atmospheres and environmental conditions. Extracted from ice sheets and glaciers, these cylindrical samples preserve a chronological record that spans hundreds of thousands of years. As snow accumulates year after year, each layer becomes a time capsule, capturing the atmospheric composition at the moment of deposition. The key to unlocking this ancient information lies in analysing the air bubbles trapped within the ice. During snowfall, tiny pockets of air become encased as the snow compacts into dense ice. Over millennia, these bubbles preserve snapshots of the atmosphere, including concentrations of greenhouse gases such as carbon dioxide, CO2, and methane, CH4. Measuring variations in these gases across different layers reveals fluctuations in Earth's climate, shedding light on periods of warming and cooling. For instance, elevated greenhouse gas levels often correlate with warmer interglacial phases, while reductions align with ice ages. Beyond gases, Ice cores contain a wealth of other climate indicators. Particulate matter like volcanic ash or dust can be embedded within layers, indicating episodes of volcanic eruptions or changes in atmospheric circulation. Isotopic analysis, particularly of oxygen, D18O, and hydrogen, DD, provides insights into past temperatures. Lighter isotopes tend to evaporate more readily during warm periods, leading to distinctive isotopic signatures that help reconstruct temperature variations over time. The stratification of ice cores also allows scientists to develop detailed chronologies. By counting annual layers, similar to tree rings, they can establish precise timelines. This dating enables correlation between climate shifts and other paleo-environmental data, enriching our understanding of how Earth's climate systems have evolved. Advancements in ice core analysis continue to refine our grasp of past climates, revealing complex interactions between atmospheric composition, temperature, and Earth's orbital parameters. As scientists interpret these layered secrets, they gain critical insights into natural climate variability and the potential trajectory of future climate change. Understanding the meticulous details preserved within ice cores forms a foundation for broader investigations into Earth's dynamic climate history, linking past, present, and future in a continuous narrative. Scientists analysing glacial landforms employ a combination of meticulous fieldwork, advanced imaging, and geochronological techniques to reconstruct past ice movements with remarkable precision. By examining features such as striations, chatter marks, roches-moutonnées, drumlins, and esca systems, researchers can infer the direction, speed, and extent of ancient glaciers. These landforms serve as tangible records, capturing the erosive and depositional processes that shaped the landscape during ice ages. High-resolution aerial photography and satellite imagery have revolutionized the ability to map and analyze these features across vast and often remote terrains. LiDAR, light detection and ranging surveys, provide detailed topographical data, revealing subtle landforms that might otherwise go unnoticed. Combining these visual tools with ground-based surveys allows for comprehensive spatial analysis, helping to distinguish between features formed by glacial activity and those resulting from other geological processes. Crucially, geochronological techniques such as optically stimulated luminescence, OSL, radiocarbon dating, and cosmogenic nuclide dating enable scientists to determine the timing of landform formation. For example, by measuring the concentration of cosmogenic isotopes like beryllium-10 and aluminum-26 in surface rocks, researchers can estimate how long ago a glacier retreated from a particular area. These temporal markers help piece together the chronology of ice sheet advances and retreats, aligning landform evidence with climatic data. Further insights arise from analysing sediment layers deposited by glaciers, known as glacial till, as well as the stratigraphy of associated sediments. Sediment cores extracted from glacial lakes or marine basins contain valuable information about past ice dynamics, climate conditions, and sea levels. Pollen, microfossils, and chemical signatures within these layers also contribute to reconstructing environmental conditions during different phases of the Ice Age. By integrating physical landform analysis with geochronology and sediment studies, scientists create detailed reconstructions of past ice movements. These reconstructions not only illuminate the behaviour of ancient glaciers, but also reveal how ice sheets responded to climatic shifts, offering essential clues to the complex interactions driving Ice Age cycles. Climate models serve as essential tools in unravelling the complexities of Ice Age conditions and their cyclical nature. These sophisticated simulations integrate a multitude of variables, such as orbital parameters, atmospheric composition, oceanic currents, and land surface features, to recreate the environmental states of past glacial periods. By inputting data derived from geological records, ice cores, and sediment analyses, researchers can generate dynamic models that project how temperature, precipitation, and ice sheet extent fluctuated over millennia. At their core, these models incorporate the principles of physics and climate science, translating astronomical cycles, like those described by Milankovich theory, into quantifiable impacts on Earth's climate system. For example, variations in Earth's tilt and orbital eccentricity influence the distribution and intensity of solar radiation reaching the surface, which models simulate to observe resultant climate shifts. These simulations also factor in feedback mechanisms, such as changes in albedo due to expanding ice sheets, or variations in greenhouse gas concentrations, creating a holistic picture of the climate's evolution. The strength of climate models lies in their ability to test hypotheses about past climate behaviour by running multiple scenarios under different initial conditions. This approach helps identify the primary drivers of glacial-interglacial cycles and understand how interconnected factors, like volcanic aerosols or oceanic heat transport, amplify or dampen climate signals. Additionally, models offer insights into regional climate variations, revealing how certain areas experienced more intense glaciation or stable conditions, thus aiding interpretations of localized geological and paleontological evidence. However, the process is inherently complex. The accuracy of these models depends heavily on the quality and resolution of underlying data, which often come with uncertainties. Moreover, capturing the full scope of Earth's climate system, especially ocean-atmosphere interactions, presents significant computational challenges. While models have become increasingly sophisticated, they continue to evolve, reflecting ongoing efforts to better simulate the intricate feedbacks and temporal scales characteristic of Ice Age cycles. This ongoing refinement brings scientists closer to understanding the deep past and predicting future climate dynamics. Reconstructing ancient Ice Age environments presents a complex puzzle, often complicated by the scarcity and delicate nature of available evidence. One of the primary challenges lies in the incomplete or disturbed nature of geological records. Over millennia, processes such as erosion, sedimentation, and tectonic shifts can obliterate or distort critical clues, making it to accurately piece together past climate conditions. For instance, glacial deposits and landforms may be buried beneath newer sediments or eroded away entirely, leaving gaps in the environmental timeline. Another obstacle stems from the difficulty in precisely dating materials associated with Ice Age environments. While techniques like radiocarbon dating have revolutionized the field, they have limitations, especially when applied to older samples beyond their effective range. This can result in broad age estimates that hinder fine-scale reconstructions of climate fluctuations and ecological shifts. Similarly, the preservation of organic materials like plant remains or bones is highly variable, depending on local conditions such as acidity, moisture and temperature, which can either preserve or rapidly degrade potential evidence. The heterogeneity of Ice Age environments also complicates reconstructions. Climate changes did not occur uniformly across the globe. Regional variations in temperature, precipitation, and ocean currents created diverse habitats and climate regimes. This spatial variability requires researchers to integrate multiple lines of evidence from different locations, each with its own preservation challenges. Moreover, disentangling natural climate variability from human influences, especially in the later stages of the Ice Age, adds another layer of complexity to interpreting environmental reconstructions. Finally, the reliance on indirect proxies, such as isotopic compositions in ice cores or sediment layers, introduces interpretative uncertainties. These proxies can be influenced by multiple factors, making it a challenge to translate them into precise environmental parameters. Together, these obstacles demand meticulous, multidisciplinary approaches, combining geology, chemistry, biology, and emerging technologies to deepen our understanding of these ancient frozen worlds, despite the inherent difficulties in reconstructing their intricate histories. Advancements in technology have profoundly transformed our grasp of Ice Age phenomena, enabling researchers to probe Earth's frozen past with unprecedented precision. Remote sensing tools, such as satellite imagery and airborne LiDAR, have revolutionized the way we map and monitor large-scale ice sheets and glacial movements. These technologies have provided detailed, high-resolution visualizations of ice sheet margins, flow patterns, and surface features, revealing subtle changes over decades and centuries that were previously indiscernible. Such data are critical for understanding how ice masses grow, shrink, and interact with their environment, shedding light on the dynamics that governed past ice ages. In addition, improvements in radiometric dating methods, including uranium series and optically stimulated luminescence, have refined the chronology of glacial events and climate fluctuations. These techniques offer more precise age estimates for ice cores, sediments, and fossil remains, allowing scientists to correlate climatic shifts with geological and biological responses with increased confidence. The ability to date events accurately has been instrumental in reconstructing the timing and pace of ice sheet expansion and retreat, as well as associated ecological changes. Ice core analysis, powered by advanced drilling technologies, provides invaluable records of atmospheric composition, temperature, and greenhouse gas concentrations spanning hundreds of thousands of years. By extracting deep ice cores from Greenland and Antarctica, scientists have uncovered intricate details about the fluctuations of carbon dioxide, methane, and other greenhouse gases during glacial-interglacial cycles, linking these variations directly to climate shifts. The integration of isotopic analysis with ice core data offers insights into temperature fluctuations and their relationship with solar insolation and other external forcings. Computational modelling has become indispensable in simulating ice sheet behaviour and climate interactions. High-performance supercomputers enable the development of complex climate models that incorporate variables such as ocean currents, atmospheric circulation, and feedback mechanisms. These models help scientists test hypotheses about the causes of glacial cycles, predict future changes, and interpret paleodata within a coherent framework. Together, these technological innovations have elevated Ice Age research from descriptive geology to a rigorous, quantitative science. They allow for nuanced reconstructions of past environments, deepening our understanding of the processes that shaped Earth's ancient icy landscapes and informing projections of future climate trajectories. Understanding the complexities of the Ice Age relies on a truly interdisciplinary approach that synthesizes insights from multiple scientific fields. Climatology provides the foundational understanding of global temperature fluctuations, orbital variations, and greenhouse gas concentrations that drove the cyclical nature of glacial and interglacial periods. Paleoclimatology, through the analysis of ice cores and sediment records, offers detailed reconstructions of past climates, capturing fluctuations in atmospheric composition, temperature, and even volcanic activity that influenced the environment. Geology and geomorphology contribute critical perspectives on landscape evolution, revealing how glaciers carved valleys, shaped mountains, and deposited sediments over millennia. These physical changes not only record ice sheet dynamics, but also influence present-day sea levels and coastal configurations. Meanwhile, glaciology focuses on the mechanics of ice sheets, their movement, accumulation, and melting, integrating physical principles to understand how ice masses expand and retreat. Biological sciences, particularly paleoecology and evolutionary biology, shed light on how flora and fauna responded to dramatic climatic shifts. They analyze fossil records, pollen deposits, and sedimentary DNA to reconstruct past ecosystems and trace migration routes. Archaeology further complements this by uncovering human interactions with Ice Age environments, revealing adaptation strategies and survival techniques. Advances in technology have fostered cross-disciplinary collaborations, such as remote sensing and computer modelling, which simulate climate patterns and ice sheet behaviours with increasing precision. These models integrate geological, climatic, and biological data, enabling researchers to test hypotheses about past environmental changes and their impacts on ecosystems. As research continues to evolve, the integration of these diverse scientific perspectives becomes increasingly vital. Each discipline contributes a piece to the puzzle, creating a comprehensive picture of the Ice Age's intricate dynamics. This collaborative approach not only deepens our understanding of past climate variability, but also informs predictions about future climate change and its potential impacts on modern ecosystems. The convergence of geology, climatology, biology, archaeology, and technology exemplifies the truly interdisciplinary nature necessary to unravel the profound mysteries of the Ice Age. The extraction and analysis of ancient DNA have revolutionized our understanding of Ice Age ecosystems, offering a molecular window into the past that complements traditional fossil and sediment records. Unlike morphological remains, which often provide limited insights into species relationships or population dynamics, ancient DNA allows scientists to trace genetic lineages, migration patterns, and adaptation strategies with remarkable precision. This molecular approach has uncovered previously unknown species, revealing a richer tapestry of biodiversity that thrived during glacial periods. By sequencing genomes from well-preserved samples, such as permafrost-preserved bones or frozen tissues, researchers can reconstruct entire population histories, identify instances of interbreeding between species, and detect genetic adaptations to cold environments. For example, studies of woolly mammoths and ancient horses reveal how populations expanded, contracted, and sometimes hybridized in response to shifting climates. These genetic insights clarify how species persisted through changing conditions, often by migrating to refugia or evolving specialized traits, thereby illuminating the resilience and vulnerability of Ice Age communities. Ancient DNA also provides a clearer picture of predator-prey interactions, revealing how populations fluctuated in tandem and how ecological balances shifted over millennia. Moreover, it helps identify the timing and causes of extinctions, shedding light on the complex interplay between climate change and human activity. This molecular data can even inform models predicting how modern species might respond to ongoing environmental pressures. By understanding the genetic capacity for adaptation observed in Ice Age survivors. In essence, the study of ancient DNA has transformed the narrative of Ice Age ecosystems from one largely based on physical remnants to a dynamic story woven from genetic threads. It allows scientists to peer into the evolutionary processes that shaped life in these frigid landscapes, highlighting both the diversity of past life and the mechanisms that enabled survival amid relentless climatic shifts. As research progresses, ancient DNA continues to deepen our appreciation of the profound interconnectedness between past ecosystems and present-day biodiversity, setting the stage for a nuanced understanding of how ecosystems respond to change. The remnants of Ice Age glaciers continue to shape Earth's landscapes and ecosystems long after the glaciers retreated. These ancient ice masses carved out valleys, fjords, and basins, leaving behind a topography that influences regional climates and habitats even today. Uplift caused by the immense weight of glaciers during their maximum extent caused land surfaces to rise, a process known as isostatic rebound, creating elevated terrains and altering drainage patterns. These changes have shaped the distribution of freshwater resources, fertile soils, and natural barriers, directly impacting current ecosystems and human settlements. The scars left by glaciers, such as moraines, drumlins, and outwash plains, serve as vital ecological niches. These landforms often host unique plant and animal communities that have adapted to the specific conditions of these terrains. For example, nutrient-rich glacial deposits foster diverse flora, which in turn support a variety of fauna. In some regions, these deposits underpin agriculture by providing fertile soils, demonstrating how ancient glacial processes continue to sustain human livelihoods. Beyond surface features, the influence of glacial remnants extends to hydrological systems. Meltwater from residual ice supplies rivers and lakes, maintaining ecological connectivity and supporting biodiversity. In areas where glaciers once persisted, the ongoing meltwater contributes to freshwater ecosystems, shaping migration patterns for aquatic species and influencing water availability for surrounding communities. The physical alterations wrought by glaciers also impact climate regulation. Large ice sheets and their meltwater influence ocean currents, atmospheric circulation, affecting regional and global climate patterns. These processes demonstrate how the legacy of Ice Age glaciers persists in the climate systems that regulate current and future environmental stability. Understanding these glacial remnants offers insight into the resilience and adaptability of ecosystems. Recognizing how landscapes have been historically transformed by ice helps us appreciate their ongoing importance and guides efforts to manage environmental change. As we reflect on the profound influence of past glaciers, we gain valuable perspective on Earth's dynamic systems, lessons that are increasingly relevant in our current climate challenges. Past ice ages serve as compelling reminders of Earth's dynamic climate system and its capacity for dramatic change. By examining these frozen epochs, we gain valuable insights into the mechanisms that drive climate variability and the resilience of life under extreme conditions. One key lesson centers on the importance of recognizing the delicate balance between greenhouse gases and global temperatures. During ice ages, fluctuations in atmospheric CO2 and methane levels played crucial roles in initiating and terminating glacial periods. Today, understanding these feedback loops underscores the necessity of monitoring greenhouse gas emissions, as even small changes can trigger significant climate shifts. The history of ice sheet expansion and retreat also highlights the profound impact of ocean currents and continental configurations on climate regulation. During glacial periods, alterations in ocean circulation patterns affected heat distribution across the globe, influencing regional climates and sea levels. Such knowledge emphasizes the importance of maintaining healthy oceanic systems and addressing human-induced disruptions like pollution and overfishing, which threaten current climate stability. Another lesson involves the resilience and adaptability of ecosystems and species. Past extinctions and migrations during ice ages reveal how life responds to rapid environmental changes, sometimes with remarkable innovation, other times with vulnerability. Studying these patterns informs modern conservation efforts, emphasizing the need to preserve genetic diversity and facilitate species migration pathways in the face of ongoing climate change. Furthermore, the archaeological evidence of human adaptation during ice ages, through technological innovations, migration strategies, and social organization, demonstrates the capacity for resilience and ingenuity amid adversity. These lessons encourage contemporary societies to develop sustainable practices and adaptive policies that enhance resilience against future climate disruptions. Ultimately, understanding the past glacial cycles illuminates the interconnectedness of Earth's climate systems and biological responses. Recognizing these lessons fosters a proactive approach to climate challenges, emphasizing the importance of scientific vigilance, adaptive management, and global cooperation to mitigate the impacts of current and future environmental changes. Today's permafrost and frozen ground serve as enduring remnants of past ice age conditions, offering a tangible link to Earth's glacial history. During the last ice age, extensive ice sheets covered large portions of the northern hemisphere, compressing the land beneath immense weight and drastically altering surface temperatures and hydrology. As these colossal glaciers advanced and retreated over millennia, they sculpted the landscape, carving out valleys, fjords, and other landforms that remain visible today. The vast expanses of permanently frozen ground that persisted through these periods are what we now call permafrost, soil, rock, and organic material that remains at or below freezing temperatures year-round. Permafrost formation is closely tied to the climate conditions of ice ages, where persistent cold temperatures prevented significant thawing. During glacial maxima, the cold climate extended permafrost deep into continental interiors, trapping ancient organic matter, including plant and animal remains. This organic material, preserved in the frozen ground, provides valuable clues about past ecosystems, climate fluctuations, and even the migration patterns of ice age fauna. As the climate warmed and glaciers receded at the end of the last ice age, some permafrost regions began to thaw, releasing stored greenhouse gases like methane and carbon dioxide, which have influenced subsequent climate variability. Today's permafrost zones are thus living archives of ice age conditions, their stability and extent reflecting the balance between current climate and the legacy of past glacial periods. The thawing of permafrost has significant implications for global climate change, as the release of trapped greenhouse gases can amplify warming trends. Conversely, in some high-latitude regions, permafrost persists due to the lingering cold climate, echoing the frigid conditions of the Ice Age. These frozen grounds continue to shape ecosystems, influence infrastructure development, and serve as critical indicators of how Earth's climate system responds to ongoing environmental shifts, directly connecting the present to the frozen epochs of the distant past. Ice Age cycles serve as fundamental drivers of long-term climate variability, shaping Earth's environmental tapestry over tens to hundreds of thousands of years. These cycles, primarily governed by subtle alterations in Earth's orbital parameters, namely eccentricity, axial tilt, and precession, alter the distribution and intensity of solar radiation reaching the planet's surface. As a result, they induce periods of cooling and warming that extend well beyond the immediate glacial and interglacial phases. During periods of increased eccentricity and axial tilt, regions near the poles receive less solar energy during winter months, facilitating the expansion of ice sheets and glaciers. Conversely, when orbital configurations favour a more direct solar influx, ice sheets retreat, ushering in warmer interglacial intervals. These cyclical shifts influence not only the extent and thickness of ice masses, but also drive broader climate patterns, including atmospheric circulation, precipitation regimes, and oceanic currents. Such variations can alter global heat distribution, impacting climate stability over millennia. The cumulative effect of these cycles manifests in a pattern of long-term climate oscillations that modulate the frequency, duration, and intensity of glacial periods. This rhythmic rhythm of climate change has historically dictated the ebb and flow of ecosystems, prompting species migration, adaptation, or extinction, and shaping the evolutionary trajectory of both flora and fauna. Changes in sea levels associated with glacial cycles, often spanning hundreds of meters, have periodically exposed or submerged continental shelves, opening or closing migration corridors and altering oceanic pathways vital for climate regulation. This intricate dance of orbital mechanics and climate feedbacks underscores how ice age cycles serve as a natural thermostat, orchestrating Earth's long-term climate variability. Understanding these cycles illuminates the complex interplay between celestial mechanics and terrestrial climate systems, revealing the profound ways in which cosmic rhythms influence our planet's environmental history. This knowledge, in turn, provides essential context for assessing current climate changes and their potential long-term impacts. The enduring imprint of Ice Age features significantly shapes modern human settlement patterns and infrastructure development. Regions once sculpted by glacial activity, such as deep valleys, fertile moraines, and expansive plains, offer both opportunities and challenges for contemporary habitation. For instance, glacially carved valleys often serve as natural corridors for transportation and urban expansion, facilitating connectivity across rugged terrains. Meanwhile, the rich, mineral-laden soils deposited by glaciers tend to foster agriculture in certain areas, supporting dense populations. However, the same features can also pose hazards. Ancient glacial deposits may destabilize foundations or increase flood risks when heavy precipitation or melting occurs. Permafrost, a hallmark of many Ice Age landscapes, exerts a profound influence on infrastructure planning. Its presence demands specialized engineering solutions to prevent subsidence and structural damage, especially as rising temperatures threaten its stability. As permafrost thaws, previously frozen ground can lead to ground collapse, damaging roads, pipelines, and buildings, thereby complicating development strategies. This phenomenon emphasizes the delicate balance between leveraging Ice Age legacy landscapes and mitigating their vulnerabilities. Moreover, the distribution of residual glacial features impacts water management systems. Moraines and outwash plains often serve as natural aquifers, supplying freshwater resources, but their irregular topography can complicate drainage and flood control efforts. Coastal zones shaped by glacial retreat are also subject to sea level changes, influencing urban planning and the resilience of coastal infrastructure. The legacy of past glaciations extends further into hazard assessment and land use policies. Recognizing areas prone to glacial lake outburst floods or landslides rooted in glacial deposits guides risk mitigation strategies. As modern societies increasingly adapt to climate variability, understanding how Ice Age features influence the landscape becomes crucial. This knowledge enables planners to optimize land use, design resilient infrastructure, and preserve natural features that continue to shape the human experience in these anciently transformed environments. The ongoing acceleration of global warming raises significant concerns about the preservation and future stability of Ice Age legacy features. Many of these features, such as ancient ice sheets, permafrost layers, and glacial landforms, serve as vital archives of Earth's climatic past, offering invaluable insights into natural climate variability. As temperatures rise, the delicate balance maintaining these features may be disrupted, leading to potential irreversible changes. For example, the melting of residual ice sheets could diminish landforms that have persisted for thousands of years, erasing key geological records of past glaciations. This loss would hinder scientists' ability to reconstruct detailed climate histories, which are essential for understanding long-term climate dynamics. Permafrost regions, often hosting preserved organic material from past ice ages, are particularly vulnerable. Thawing permafrost can release vast quantities of stored greenhouse gases such as methane and carbon dioxide, amplifying current warming trends. Such feedback loops not only accelerate climate change, but also threaten to alter the very climate signals embedded within these frozen layers, complicating future climate modelling efforts. Moreover, the destabilization of permafrost can lead to ground subsidence, affecting landscapes and ecosystems that have remained stable since the Ice Age, disrupting habitats and human settlements alike. The potential loss of glacial features also impacts sea level predictions. As residual glaciers melt, contributions to sea level rise become more uncertain, especially if feedback mechanisms accelerate ice loss. These changes could mirror or even surpass the impacts observed at the end of past glaciations, but with unprecedented rapidity. Consequently, the erosion of Ice Age legacy features due to current warming complicates the interpretation of paleo-environmental data, making it more challenging to distinguish between natural variability and human-induced change. Understanding the fate of these features under warming conditions is crucial, not only for preserving Earth's geological heritage, but also for refining models that predict future climate trajectories. Preserving these archives allows scientists to better anticipate how ongoing climate shifts might reshape our planet in centuries to come, emphasizing the importance of integrating past climate responses into modern predictive frameworks. Studying ice ages provides invaluable insights that enhance the accuracy and reliability of climate prediction models. By examining the geological remains left by glacial periods, such as sediment layers, ice cores and landforms, scientists gain a detailed record of past climate variability. These natural archives encapsulate information on atmospheric composition, temperature fluctuations, and oceanic changes over tens of thousands of years. Ice cores, in particular, serve as time capsules, trapping gases like carbon dioxide and methane, thus allowing researchers to reconstruct ancient greenhouse gas concentrations with remarkable precision. This historical perspective reveals how the Earth's climate system responded to various forcing mechanisms, including orbital changes and volcanic activity, helping scientists identify patterns and thresholds that triggered glacial and interglacial shifts. Furthermore, the dynamic behavior of ice sheets during past ice ages informs models about feedback processes and nonlinear responses within the climate system. For instance, understanding how ice sheet growth and decay influence sea levels and albedo effects enables better predictions of potential future sea level rise under different greenhouse gas emission scenarios. The study of erosion and deposition patterns left by glaciers also aids in calibrating models of surface processes and sediment transport, which are integral to simulating climate interactions and land surface feedbacks. Incorporating data from Ice Age deposits enhances the resolution of climate models by anchoring simulations in real-world examples of climate change over millennia. This historical context helps refine the sensitivity of models to various forcing factors, making projections more robust. It also fosters a deeper understanding of the potential timings and magnitudes of climate shifts, critical for preparing for future climate variability. As models become more sophisticated, they are better equipped to forecast the complex interplay of atmospheric, oceanic, and terrestrial processes. Consequently, the study of ice ages not only illuminates Earth's climatic past, but also provides a crucial foundation for anticipating and managing future climate challenges. Ice Age deposits serve as invaluable repositories of Earth's geological and environmental history, playing a crucial role in the exploration and management of natural resources. These deposits, composed of sediments, till, and other sediments laid down by glaciers and ice sheets, contain a wealth of information about past climates, vegetation, and mineral distributions. Their study allows geologists and resource managers to identify areas with rich mineral deposits, including ores, coal, and hydrocarbons, which often accumulate in glacially influenced terrains. For instance, the erosion and deposition processes associated with glacial movement often concentrate valuable minerals in specific zones, making these regions prime targets for exploration. In addition to mineral resources, Ice Age deposits underpin the identification of aquifers and groundwater reserves. Sediments from glacial meltwater channels and till plains often form porous, permeable layers, capable of storing significant amounts of fresh water. Understanding the stratigraphy of these deposits helps delineate aquifer boundaries and assess the sustainability of groundwater extraction, especially in regions where modern water supplies depend heavily on ancient glacial deposits. Furthermore, Ice Age deposits influence land use planning and environmental management. Areas covered by glacial till and sediments can impact soil fertility and stability, affecting agriculture and construction. Recognizing the extent and composition of these deposits guides sustainable land management practices, preventing issues such as land subsidence or erosion. In coastal zones, remnants of glacial deposits influence sea level change assessments, helping predict future shoreline shifts and inform mitigation strategies against sea level rise. The study of Ice Age deposits also informs environmental conservation efforts. By analysing past climate conditions preserved in these sediments, scientists can better understand how ecosystems responded to climate fluctuations, guiding efforts to preserve biodiversity amid ongoing climate change. Overall, these deposits are not merely remnants of a frozen past. They are dynamic records that shape our understanding of Earth's resource potential and environmental resilience, guiding responsible exploration and sustainable management in a changing world. This intricate interplay between geology and resource management underscores the importance of Ice Age deposits, bridging past processes with present-day needs. As we probe deeper into these ancient layers, we uncover insights crucial for navigating future challenges and opportunities. The discovery of remarkable fossils and artifacts from the Ice Age has profoundly expanded our understanding of the life that thrived during this frigid epoch. Among the most significant finds are the bones of massive megafauna such as the mammoth, mastodon, and saber-toothed cats. These fossils reveal not only the characteristics and adaptations of these creatures, but also shed light on their ecological roles within Ice Age ecosystems. For instance, well-preserved mammoth remains, like those uncovered in Siberia's permafrost, have provided insights into their diet, migration patterns, and even instances of disease or injury, painting a vivid picture of their struggle for survival amid harsh conditions. Notably, the discovery of the Lascaux cave paintings in France offers a glimpse into the cultural life of Ice Age humans. These intricate depictions of animals such as aurochs and horses demonstrate the importance of hunting and spiritual symbolism in early human societies. Such artifacts underscore the complex relationship between humans and their environment, revealing not just survival strategies, but also a burgeoning artistic expression and ritual practice. The discovery of the Philendorf Venus figurine provides further evidence of early human symbolic thought and social structure. Carved from limestone and adorned with detailed features, these figurines suggest that Ice Age humans engaged in rituals related to fertility, survival, or spiritual beliefs, offering a glimpse into their worldview. In recent decades, the excavation of cave sites like Altamira and Chauvet has unearthed extraordinary wall paintings, some dating back over 30,000 years. These artworks depict animals and abstract symbols, illustrating the cognitive and cultural evolution of Ice Age humans. Each discovery not only enriches our understanding of the fauna and flora of the period, but also reveals the depth of human ingenuity and adaptation in a challenging world. Collectively, these fossils and artifacts serve as vital keys to unlocking the mysteries of life during the Ice Age, connecting us to a distant, resilient world. Among the most significant archaeological sites illuminating Ice Age life are the Labrea Tarpits in Los Angeles. Unlike traditional fossil deposits formed in sedimentary layers, these tar pits represent a natural trap that preserved a remarkable snapshot of Pleistocene megafauna and smaller creatures, offering invaluable insights into the biodiversity ecology and survival strategies of the period. The sticky asphalt seeped to the surface over thousands of years, ensnaring animals that wandered into its vicinity, often unable to escape. This process resulted in an extraordinary assemblage of well-preserved bones, many with soft tissue impressions, which have been meticulously excavated and studied. The Labrea discoveries expanded our understanding of Ice Age fauna beyond mere skeletal remains. The abundance of species, ranging from mammoths and mastodons to dire wolves, saber-toothed cats, and giant ground sloths, paints a vivid picture of the complex predator-prey interactions that shape the ecosystem. By analysing these remains, researchers have reconstructed food webs, migration patterns, and territorial behaviours, revealing how these animals adapted to fluctuating climates and resource availability. The preservation of juvenile and injured individuals also provided clues about survival challenges and the role of environmental stresses. Furthermore, the context of the finds has shed light on the timing and pace of Ice Age extinctions. Many species excavated from the tar pits disappeared shortly after the last glacial maximum, implicating climate change and human activity as driving forces. The preservation of tools and evidence of human interaction within the same layers deepened our understanding of early human hunting practices and adaptation strategies in a rapidly changing world. The significance of the Labrea Tarpits extends beyond paleontological curiosity. They serve as a window into the delicate balance of Ice Age ecosystems and the factors that led to the rise and fall of megafauna communities. These discoveries continue to inform models of climate change, extinction dynamics, and human-environment interactions, emphasizing how natural traps can preserve a wealth of information for future generations of scientists. Their importance lies not only in what they reveal about the past, but also in how they help us understand ongoing ecological shifts today. The discovery of woolly mammoth stands as a pivotal moment in understanding the remnants of Ice Age life, offering invaluable insights into the environment, ecology, and human interaction during this frigid epoch. These well-preserved fossils, often found in permafrost regions, provide a remarkably detailed snapshot of the species that once roamed the icy plains. Their preservation, sometimes including soft tissues, hair, and even stomach contents, allows scientists to reconstruct not only the physical characteristics of these giants, but also aspects of their diet, health, and behaviour. Such data deepens our grasp of the ecological webs that sustained Ice Age megafauna and the climatic conditions that shaped their existence. Beyond ecological reconstruction, woolly mammoth remains also serve as direct evidence of adaptation strategies. Their thick fur, fat layers, and specialized limb structures reveal how they evolved in response to extreme cold, offering clues about evolutionary pressures faced by megafauna in glaciated landscapes. These insights help clarify the broader patterns of species adaptation and extinction, especially as many mammoth populations vanished toward the end of the Ice Age, a process intertwined with climate shifts and human hunting. The significance of these discoveries extends further into understanding early human life. Numerous sites where mammoth remains are found often contain tools, weapons, or carvings associated with human activity, indicating that these creatures were central to Ice Age survival strategies. The remains thus act as a gateway to exploring how humans hunted, scavenged, and possibly domesticated or utilized mammoth resources, shaping their cultural practices. These interactions reveal the ingenuity of Ice Age humans in adapting to their environment and exploiting available resources. In essence, woolly mammoth remains are more than mere fossils. They are time capsules that illuminate the complex interplay of climate, ecology, and human ingenuity during the Ice Age. Their study continues to refine our understanding of a world transformed by relentless climatic upheavals, making each discovery a vital piece in the puzzle of our ancient past. Cave paintings and carvings serve as remarkable windows into the minds and lives of Ice Age humans, offering invaluable insights that extend beyond mere survival. These ancient artworks reveal complex aspects of cultural expression, spiritual beliefs, social organization, and interactions with the environment. Unlike other archaeological artifacts, images etched and painted onto cave walls encapsulate a vivid narrative of human experience, often depicting animals, hunting scenes, and symbolic motifs. The detailed depictions of megafauna such as mammoths, bison, and reindeer highlight the central role these creatures played in daily life, not only as sources of food and materials, but also as symbols imbued with spiritual significance. The choice of subjects suggests a deep understanding and reverence for the environment, indicating that Ice Age humans were keen observers of their surroundings. Such artworks often served ritualistic or educational purposes, possibly guiding hunting practices or reinforcing social bonds within communities. Analysis of the stylistic features and placement of these carvings and paintings also illuminates aspects of cognition and communication. The use of perspective, symbolism, and narrative sequences points to sophisticated cognitive abilities, including abstract thought and shared cultural conventions. In some cases, the recurring motifs and patterns may reflect early attempts at recording stories or conveying collective memories, establishing a cultural continuity that transcended generations. Furthermore, certain cave sites reveal evidence of ritualistic behaviour, such as red ochre markings and deliberately arranged carvings, implying that these spaces held spiritual or ceremonial significance. The integration of art into the natural landscape suggests a worldview in which humans saw themselves as interconnected with the animals and spirits represented in their artwork. These artistic expressions serve as a cultural record, complementing physical artifacts like tools and dwellings. They help reconstruct social structures, belief systems, and environmental interactions during the Ice Age, creating a richer, more nuanced picture of human adaptability and ingenuity in a challenging climate. As we examine these ancient images, we gain a profound understanding of how early humans perceived and related to their world, laying the groundwork for interpreting subsequent cultural and technological developments. Major archaeological sites have served as invaluable gateways to understanding Ice Age environments, offering tangible snapshots of a distant frozen world. These sites, often preserved in ice, caves, or sediments, have revealed a wealth of information through discoveries of tools, bones, shelters, and art that illuminate how early humans and animals interacted with their surroundings. Their strategic locations, such as caves in Europe, shelters in Siberia, and lakeside campsites, have preserved evidence remarkably well, allowing researchers to reconstruct climate conditions, vegetation patterns, and animal populations that characterize different phases of the Ice Age. The significance of these sites extends beyond mere artifacts. They serve as chronological anchors, providing precise dating through radiocarbon and other techniques. This temporal context helps establish the sequence of environmental changes alongside human adaptations. For example, the discovery of mammoth remains alongside sophisticated tools indicates not only the presence of large megafauna, but also the technological ingenuity of Ice Age humans in exploiting available resources. Similarly, cave paintings and carvings depict fauna and landscapes, offering visual records of flora and fauna that no longer exist, thus enriching our understanding of paleoecology. Sites such as the Denisova Cave in Siberia have uncovered genetic material from ancient humans, revealing migration pathways and interbreeding events that shaped human evolution. These revelations challenge previous assumptions, emphasizing the importance of archaeological sites as repositories of biological and environmental data. Furthermore, sediment layers and pollen analysis from these sites provide insights into climate fluctuations, helping to reconstruct temperature ranges, rainfall patterns, and vegetation zones during various Ice Age periods. As technological tools become more sophisticated, the role of archaeological sites in Ice Age research continues to expand. They serve as natural laboratories where multidisciplinary approaches, combining archaeology, paleontology, geology, and genetics, intersect. These sites are not only windows into the past, but also keys to understanding how climate change, ecological shifts, and human ingenuity intertwined in shaping the legacy of the Ice Age landscape. Their ongoing excavation and study promise to deepen our grasp of this complex chapter in Earth's history. Recent technological innovations have profoundly transformed Ice Age research, opening new frontiers in understanding this complex epoch. Advances such as high-resolution radiocarbon dating, LIDAR scanning, and genomic sequencing have enabled scientists to refine timelines and uncover details previously hidden beneath layers of sediment or ice. These tools have significantly improved the accuracy of dating artifacts, fossils, and sediment deposits, allowing researchers to pinpoint migration patterns and climatic shifts with unprecedented precision. For example, the ability to analyze ancient DNA from both humans and megafauna has illuminated intricate relationships between species, revealing migration routes and adaptive strategies that shaped survival during fluctuating glacial periods. LIDAR technology, originally developed for topographical mapping and military applications, has become instrumental in revealing subtle landscape features concealed beneath vegetation or ice sheets. By generating detailed three-dimensional maps of Paleolithic sites, researchers can identify previously overlooked habitation areas, tool assemblages, or migration corridors. This has led to discoveries of early human settlements in regions once thought inhospitable, broadening our understanding of human resilience and adaptability. Similarly, remote sensing satellites equipped with multispectral imaging facilitate large-scale surveys of sediments and landforms, helping trace glacial extents and retreat patterns over millennia. Furthermore, advancements in computational modelling have transformed the study of ice sheet dynamics. By integrating climate data, ocean currents, and geological records into sophisticated simulations, scientists can reconstruct past climate scenarios and predict how ice sheets responded to various forcing factors. These models help clarify debates about the timing and mechanisms behind rapid glacial advances or retreats, enriching our understanding of ice sheet stability. Genomic technologies have also played a pivotal role in revealing the genetic diversity and migration pathways of Ice Age species and humans. Sequencing ancient DNA from well-preserved remains offers insights into adaptation, population bottlenecks, and interspecies interactions. These breakthroughs have redefined timelines of human dispersal and extinction events, illustrating the dynamic interplay between climate change and biological responses. The integration of these technological advances continues to challenge long-held assumptions and inspire new hypotheses. As tools evolve, they promise to deepen our grasp of Ice Age complexities, unveiling a more nuanced narrative of Earth's frozen past. The pursuit of understanding the Ice Age through its myriad discoveries has not been without its share of debates and controversies. Central to these discussions is the interpretation of archaeological and geological evidence, which often reveals complex and sometimes conflicting narratives about the timing, extent, and impact of glacial periods. One prominent area of contention revolves around the precise chronology of glacial advances and retreats. While radiocarbon dating and ice core analysis have provided critical timelines, discrepancies in dating methods and the incomplete nature of the fossil record lead some researchers to question the synchronization of global ice sheet fluctuations. These debates influence how scientists reconstruct the pace of climate change and its regional variations, shaping broader models of Earth's climatic history. Another ongoing controversy involves the causes behind abrupt climate shifts observed during the late Pleistocene. Some scholars argue that these rapid transitions, such as the Younger Dryas, were primarily driven by freshwater influxes disrupting ocean currents, while others posit an amplified response to orbital variations or volcanic activity. The debate hinges on interpreting proxy data from sediments and ice cores, with each side emphasizing different mechanisms that could have triggered such swift changes. These disagreements are not merely academic, they influence how we understand the stability of current climate systems and the potential for sudden shifts. Additionally, the interpretation of fossil evidence regarding megafaunal extinctions remains contentious. While climate change undoubtedly played a role, many researchers debate the extent to which human activity, such as hunting and habitat alteration, accelerated these declines. The timing of human arrival in different regions complicates this narrative, leading to debates about causality versus coincidence. This underscores the importance of integrating multiple lines of evidence to form a nuanced picture of the interplay between natural climate variability and anthropogenic influences. These debates reflect the dynamic nature of paleoclimatology and underscore the importance of continuous research. They challenge scientists to refine methodologies and re-examine assumptions, ultimately enriching our understanding of Earth's climatic past. Such discussions remind us that even well-established discoveries remain open to reinterpretation as new evidence emerges, highlighting the evolving story of our planet's frozen epochs. These groundbreaking discoveries serve as vital keys to unlocking the intricate history of Earth's past climates, offering nuanced insights that extend beyond the mere chronology of ice sheet advances and retreats. By precisely dating ancient sediments, ice cores, and fossil remains, scientists can reconstruct detailed climatic fluctuations that occurred over hundreds of thousands of years. Such data reveal patterns of temperature variability, atmospheric composition, and oceanic changes, enabling researchers to identify correlations between orbital cycles, greenhouse gas concentrations, and climate shifts. The remarkable preservation of ancient flora and fauna within ice deposits and sediment layers provides direct evidence of how ecosystems responded to changing temperatures and environmental conditions. For example, Shifts in species distributions and the timing of migrations or extinctions help delineate the thresholds of climate tolerance and reveal the pace of ecological adaptation. These findings refine models of how climate variability influences biological resilience and vulnerability, offering predictive insights relevant to contemporary climate change. Furthermore, the study of glacial deposits and landforms has illuminated the extent and rate of ice sheet movements, refining our understanding of ice dynamics under different climatic scenarios. This in turn refines sea level reconstructions, illustrating the profound impact of ice age cycles on continental coastlines and global geography. Such reconstructions have proven invaluable in contextualizing current sea level rise and coastal vulnerabilities. In addition, interdisciplinary approaches integrating climate modeling, geology, paleobotany, and archaeology have expanded our comprehension of how climate changes have shaped human evolution, migration routes, and cultural development. These discoveries underscore the interconnectedness of climatic and biological systems over geological timescales. As research advances, scientists are continually uncovering new layers of complexity within Earth's climatic history. These insights not only deepen our understanding of past climate variability, but also enhance predictive models essential for addressing current and future climate challenges. The evolving picture underscores the importance of integrating paleoclimatic data into broader Earth system science, ultimately informing strategies for resilience in a warming world. The pursuit of understanding Ice Age phenomena faces a dynamic landscape of scientific frontiers and formidable challenges. As researchers delve deeper into Earth's glacial history, they grapple with the complexity of disentangling intertwined climate signals preserved within geological records. One significant frontier lies in refining chronological frameworks, dating ancient ice cores, sediments, and fossils with increasing precision. Advances in isotopic analysis and high-resolution stratigraphy have opened new avenues, yet uncertainties remain when correlating data across different regions and timescales. This intricacy complicates efforts to reconstruct the precise timing and pace of climate shifts, such as the onset and termination of glacial periods. Another critical challenge involves interpreting the vast, often incomplete, archives of past climate data. While ice cores from Greenland and Antarctica offer invaluable insights into atmospheric composition and temperature fluctuations, they represent only a fraction of the global picture. Expanding this knowledge requires integrating diverse proxies, marine sediments, terrestrial deposits, and cave records, each with their own complexities and dating constraints. This integration demands sophisticated models capable of synthesizing disparate data sets into cohesive climate reconstructions. The intricacies of ice sheet dynamics themselves present ongoing hurdles. Modern climate models strive to simulate ice sheet responses to warming, but accurately capturing processes like basal sliding, calving, and subglacial hydrology remains difficult. These sub-processes critically influence ice sheet stability and have direct implications for future sea level rise predictions. Incorporating feedback mechanisms, such as albedo effects and ice-climate interactions, adds further layers of complexity to climate models. Finally, the challenge extends to understanding how ice age cycles interacted with Earth's biosphere and human societies. This requires not only paleoclimatic data, but also insights from archaeology, genetics, and ecology, fields that must converge to illuminate how ancient populations responded to climate variability. Bridging these disciplines and translating past patterns into future projections constitute some of the most ambitious frontiers in climate science today. As technology advances, so too does our capacity to confront these challenges, promising a richer understanding of Earth's frozen epochs. Advancements in artificial intelligence, AI, and machine learning (ML) are poised to revolutionize our comprehension of ice age cycles by enabling unprecedented analysis of complex climate data. These technologies excel at detecting subtle patterns within vast datasets, patterns that often elude traditional statistical methods. By integrating proxy records such as ice cores, sediment layers, and fossil distributions, AI algorithms can reconstruct detailed timelines of climate fluctuations with higher precision. For example, ML models can identify cycles or triggers in orbital variations, greenhouse gas concentrations, and oceanic changes, revealing the nuanced interplay of factors driving glacial advances and retreats. Furthermore, AI-driven simulations can incorporate multiple variables simultaneously, allowing researchers to test various hypotheses about ice age dynamics under different boundary conditions. Such models can simulate how minor shifts in Earth's orbit or atmospheric composition might influence long-term climate patterns, providing insights into the thresholds that trigger transitions between glacial and interglacial periods. As new data from ongoing drilling projects, satellite observations, and climate proxies are integrated, machine learning systems continuously refine their predictions, increasing reliability and depth of understanding. Another promising application involves the use of neural networks to analyze ancient biological and geological records, offering clues about how ecosystems and landscapes responded to climate shifts. This can shed light on the feedback mechanisms that either amplified or dampened climatic changes, informing models of future climate stability. Additionally, AI can help identify regional disparities in ice sheet behavior, revealing how localized factors contributed to global patterns. By harnessing AI and ML, scientists can also improve the dating accuracy of key events in ice age history, such as rapid deglaciations or sudden climate reversals. These enhanced chronological frameworks are vital for correlating climate events with potential external forcings, including volcanic eruptions or solar variability. Collectively, these technological advances deepen our grasp of past climate variability, equipping us with vital knowledge to better anticipate future climate trajectories in a warming world. Studying past ice ages offers critical insights into the sensitivities and feedback mechanisms of Earth's climate system, which are essential for refining future climate projections. By examining the timing, duration, and rapidity of glacial and interglacial transitions, scientists can identify the thresholds and tipping points that may signal abrupt climate shifts in the future. These historical records reveal how interconnected components, such as ice sheet mass balance, atmospheric greenhouse gases, and ocean circulation, respond to changing conditions, allowing models to incorporate more realistic interactions and nonlinear behaviors. Ice core and sediment records have been instrumental in reconstructing past atmospheric compositions, providing benchmarks against which model outputs can be validated. For instance, understanding how greenhouse gas concentrations fluctuated in tandem with temperature during past climate cycles helps calibrate the sensitivity of climate models to trace gas variations. The detailed chronology of ice sheet advances and retreats also informs predictions of how contemporary ice masses may respond to ongoing warming, including potential nonlinear disintegration events and their implications for sea level rise. Furthermore, paleo-ecological data, such as shifts in flora, fauna, and human populations, highlight the importance of ecological resilience and adaptation. These lessons guide models to better simulate feedbacks between climate and biosphere processes, including carbon cycle dynamics. Recognizing the pace of past climate changes, particularly during abrupt events like Dansgaard-Oeschger oscillations, underscores the potential for rapid transformations that challenge linear projections. This knowledge encourages the development of models capable of capturing sudden, large-scale shifts in climate states. By integrating these detailed reconstructions with advances in computational power and observational data, climate scientists are continuously refining models to better simulate the complex dynamic interactions of Earth's climate system. Such improvements are vital for generating more accurate, reliable forecasts of future climate change, ultimately helping societies prepare for and mitigate potential impacts rooted in Earth's deep climate history. Refining climate models to improve predictions of long-term Earth system changes hinges on integrating increasingly sophisticated data and understanding complex feedback mechanisms. Advances in paleoclimate reconstructions, derived from ice cores, sediment records, and other proxies, provide vital benchmarks that help calibrate models against past climate variations, the dramatic shifts observed during ice age cycles. These reconstructions reveal intricate relationships between greenhouse gases, orbital variations, and climate responses, prompting model developers to incorporate detailed representations of these interactions. Furthermore, enhanced computational power enables the simulation of Earth's climate system at higher resolutions, capturing small-scale processes such as cloud formation, oceanic eddies, and permafrost feedbacks. These finer details are crucial, as they often amplify or dampen larger climate signals, influencing long-term projections. Incorporating dynamic ice sheet models into broader climate frameworks allows scientists to better understand how ice mass changes contribute to sea level rise and regional climate shifts, creating a more integrated picture. In addition, ongoing research into Earth's biogeochemical cycles, such as carbon and nitrogen fluxes, has led to the development of models that more accurately reflect how biological productivity and human activities influence atmospheric composition over millennia. Integrating these processes helps predict how future emissions and land use changes might interact with natural climate variability. Model validation has also benefited from international efforts to create comprehensive climate data archives and collaborative simulation experiments. These shared resources enable scientists worldwide to test models against a variety of climate scenarios, fostering improvements in reliability and robustness. As our understanding of Earth's climate feedbacks deepens, models become increasingly capable of simulating the delicate balance of factors driving long-term change. In this evolving landscape, collaboration among climate scientists, geologists, ecologists, and policymakers is essential. Their collective efforts ensure that models remain grounded in empirical evidence, refining our ability to anticipate future shifts in Earth's climate system with greater precision and confidence. International collaborations serve as a vital engine propelling advancements in ice age and climate science, uniting researchers across disciplines and borders to unravel Earth's frozen past. The complexity of ice age phenomena, spanning glacial dynamics, paleoclimatic reconstructions, and paleo-ecological shifts, demands diverse expertise and extensive data sharing that no single institution or nation can fully provide alone. Collaborative efforts facilitate the pooling of resources, enabling large-scale projects such as drilling deep ice cores, constructing global climate models, and mapping ancient landscapes with unprecedented resolution. Through joint ventures like the European Project for Ice Coring in Antarctica, EPICA, or the International Ocean Discovery Programme, IODP, scientists can synchronize data collection and analysis, fostering a comprehensive understanding of climate fluctuations over millions of years. These partnerships also promote standardization of methodologies, ensuring that findings are comparable and integrable across different regions and disciplines. The integration of archaeological, geological, and climatological data from multiple countries enhances the accuracy of reconstructions, revealing patterns of human migration, volcanic activity, and environmental change during the Ice Age. Moreover, international collaborations enable rapid dissemination of discoveries, stimulating global dialogue and innovation. They often involve training programs that build capacity in less developed nations, broadening the scope of research and ensuring that diverse perspectives inform scientific interpretations. Such cooperation also plays a crucial role in addressing contemporary climate challenges, as lessons learned from past climate variability inform projections of future change. These joint efforts extend beyond research, fostering a shared sense of stewardship for Earth's history and environment. As scientists, policymakers, and educators work together through international networks, they create a foundation for informed decision-making that balances scientific insight with societal needs. By uniting around the common goal of understanding our planet's glacial past, collaborations not only deepen our knowledge, but also bolster the global commitment to sustainable stewardship of Earth's climate and landscapes. Public awareness and education about Ice Age science possess transformative potential to influence policy and conservation efforts in profound ways. When communities understand the intricacies of glacial dynamics, the history of Earth's climate fluctuations, and the delicate balance that sustains permafrost and ice sheet stability, they become active participants in shaping sustainable strategies. Knowledge about how past climate shifts drove dramatic landscape changes and affected ecosystems underscores the importance of preserving these fragile regions for future generations. Educating the public about the role of glaciers and permafrost in regulating global climate can foster a sense of stewardship. For example, awareness of how melting permafrost releases trapped greenhouse gases like methane highlights the feedback mechanisms that can accelerate climate change. When individuals grasp these scientific principles, they are more likely to support policies aimed at reducing emissions, protecting critical habitats, and funding scientific research. Such understanding also dispels misconceptions, encouraging informed debates on issues like geoengineering or resource extraction in glacial regions. Effective science communication can empower local communities living near ice-rich landscapes, emphasizing the importance of sustainable land use, infrastructure resilience, and adaptation strategies. In regions vulnerable to permafrost thaw, education campaigns can promote practices that minimize environmental disruption and safeguard infrastructure. Moreover, public engagement through citizen science initiatives, such as monitoring glacier retreat or permafrost temperature changes, can generate valuable data and foster a sense of shared responsibility. The influence of well-informed societies extends to policymakers, who often rely on public support to enact legislation. When scientific literacy about Ice Age phenomena is widespread, policymakers are more inclined to prioritize climate resilience, conservation funding, and international cooperation on Arctic preservation. Ultimately, cultivating a scientifically literate public creates a ripple effect, driving innovation, fostering resilience, and encouraging global efforts to address the pressing challenges facing Earth's glacial and permafrost regions in an era of rapid climate change. As global temperatures continue to rise, the implications for Earth's glacial and permafrost regions become increasingly profound. These icy reservoirs serve as vital indicators of climate stability, and their potential transformation holds significant consequences for the planet's future. Warming trends threaten to accelerate the melting of glaciers worldwide, which would contribute to rising sea levels at a scale that could reshape coastlines and displace communities. The loss of glaciers also diminishes freshwater supplies for millions, affecting agriculture, drinking water, and ecosystems dependent on seasonal meltwater flows. Permafrost regions, covering vast expanses of polar and subpolar areas, are particularly vulnerable. As temperatures climb, permafrost begins to thaw, releasing vast quantities of stored organic material. This decomposition releases greenhouse gases like methane and carbon dioxide, potent drivers of further climate warming. The feedback loop created by this process could amplify global warming, making it more difficult to predict and manage future climate scenarios. Thawing permafrost destabilizes ground structures, leading to erosion and infrastructure damage, impacting indigenous communities and economic activities. The destabilization of these frozen regions also has ecological implications. As ice retreats, habitats for specialized flora and fauna shrink or shift, threatening biodiversity and altering migration patterns. In some cases, newly exposed land becomes vulnerable to erosion or invasive species, disrupting existing ecosystems. Moreover, the loss of reflective ice surfaces accelerates heat absorption by darker land or water surfaces, intensifying regional and global warming. Understanding the potential trajectory of these changes is crucial for developing adaptive strategies. Advances in remote sensing and climate modelling allow scientists to better predict the pace of glacial melt and permafrost degradation. These insights inform policy decisions, emphasizing the urgency of reducing greenhouse gas emissions to mitigate irreversible environmental shifts. As evidence mounts, the need to comprehend the complex interplay between climate change and Earth's icy regions becomes ever more urgent, underscoring their role as both barometers and drivers of planetary health. Looking ahead, ongoing research promises to deepen our grasp of these processes, revealing nuances that could reshape our understanding of Earth's climatic past and future. As our understanding of past ice ages continues to deepen through ongoing research and technological advancements, it becomes clear that future discoveries hold the potential to fundamentally reshape our perception of Earth's climatic history and its trajectory. Enhanced paleoclimatic proxies, such as ice core analyses, sediment records, and novel isotopic techniques, promise to refine timelines and clarify the mechanisms driving abrupt climate shifts. For instance, uncovering previously unknown volcanic or solar activity episodes could illuminate their roles in triggering or terminating glacial periods, challenging or confirming current models that emphasize orbital variations and greenhouse gas feedbacks. Emerging techniques in DNA analysis of ancient flora and fauna might also revolutionize our understanding of ecological resilience and extinction patterns during glacial cycles. Discovering new species or genetic data from long-extinct organisms could reveal adaptive strategies previously unrecognized, providing insights into how ecosystems responded to rapid climate fluctuations. Such knowledge might inform predictions about how contemporary species could adapt, or fail to adapt, to ongoing climate change. Advances in climate modelling, especially those integrating complex interactions between atmosphere, oceans, biosphere and cryosphere, are likely to produce more accurate simulations of past climates. These enhanced models could lead to the identification of hitherto unrecognized feedback mechanisms, such as the influence of subglacial lakes or permafrost dynamics, which may have played critical roles during past transitions. Recognizing these factors could alter our understanding of the stability of current ice sheets and the potential for rapid ice loss in the future. Additionally, as new drilling projects and remote sensing technologies push the boundaries of accessible geological records, we may discover previously unexamined regions that hold clues to regional climate variability and ice sheet behavior. These findings could challenge existing paradigms about the uniformity of glacial cycles and reveal a more complex, mosaic-like history of Earth's ice ages. Ultimately, future discoveries will deepen our grasp of the intricate web of factors shaping Earth's climate, offering both cautionary lessons from the past and guidance for navigating a changing future. Such insights will be invaluable in informing climate policy, conservation efforts, and our broader understanding of Earth's dynamic systems.